Hello.
Hi, Rishabh.
Hi, am I audible okay?
Hey, I can hear you, yes.
Okay. Do we plan to release this as a video or something? Like,
Yes, we'll,
okay.
it's getting recorded already.
Okay. Yeah. Maybe I can. So, can I keep my camera open at the start and at the end? I don't know. Maybe I'll save some bandwidth.
Yeah, you don't have to switch on your camera. Like just,
That's
you can share the screen.
yeah. Let me just try that. Just 1 second. So, can you see my screen? Like, are you seeing
Yes.
the, okay, is this a full screen view or you are seeing my speakers view?
I think it is a full screen.
Oh, great. Yeah. Thank you.
All right, so we are almost in time. Yeah, welcome everyone. This is the second session. It's likely that many folks are still in the other side, and that's why we have only 14 people here. We'll start the session with Rishabh finding cracks in analysis and out. And the other thing is Zoom is acting up a little bit. I'm unable to make Johannes as a co-host. We'll figure out that thing later. But yeah, Rishabh, go ahead and you can get started.
Okay. Thank you, Aditya. Hi, everyone. I'm Rishabh. I work on GPU compilers at AMD. Today, I'm going to talk about finding cracks between the analysis. Let me add some more precision to this title, mostly about which cracks we are talking about. So today I'll be discussing about finding the bugs caused by the interaction between the analysis. So the cracks I'll be talking about are more or less the bugs which arise due to the interaction between different analysis. Yeah. Let us quickly revisit how LLVM generates and optimizes its IR and the way it generates assembly from its IR. Yeah. So this is a abstracted bird's eye view of LLVM. The source is translated into the IR by the front end. The IR is then optimized by various transformations, which are backed up with information from analysis. The IR is then translated into the assembly by the backend. There are lot and lots of moving parts here, and there are lot of places where things can go wrong. Let us quickly take a look at all the possibilities where things may not go the way that we expect. Maybe the front end is generating some IR which we don't want it to generate. Maybe the backend generated some assembly that may be right, but that is not what we desire. Maybe it's less optimized. Maybe that's not expected or something on those direction. But yeah, maybe the IR that is transformed is not equivalent in a way that maybe like equivalent in with respect to the correctness. And then we can say that maybe the analysis results are wrong. But for all these things, like for the compilers that are already used in production, like LLVM and GCC, these things have already been figured out and worked upon. If the front end is not generating the right IR, then it is very probable that someone must have already fixed that, because someone might have already noticed that. So in this talk, we'll keep ourselves confined to analysis, and we will focus more on the section that we discuss in the title, the interaction between different analysis. And slowly we'll be scoping out other details and to drive our focus into the area which we are interested in. So after removing all the things, now we know that, yeah, the transformations uses analysis to do something, to do some transformations. Now these transformations are not one single big transformation, but I guess something on chat, right? Okay, great. Yeah, I won't be seeing chat more. Yeah, it's distracting, but no worries. So yeah, so we don't have a big transformation. Transformations use analysis, but yeah, we don't have a big transformation. What we have is we have different unit transformations which are arranged serially. These arrangement can have back edges so that we can rerun transformation. Now, to again reduce our scope, we'll just talk about a single transformation so that we can just focus on a single transformation that uses an analysis, and then so that we can just dive into the section which we are interested in. So as we saw that transformation are sort of serially arranged, that each transformation act on the IR and it transform it to something else, it optimizes it to something else. But we cannot say the same about analysis. Let's consider analysis. Bit vaguely, we can say that, yeah, there are a lot of analysis. But this also defines that, yeah, there is no single big analysis which tells us everything, but yeah, there are lots of many analysis which work in some way to give us some results. But unlike the transformation, these analyses are not serially arranged. Instead, they form a DAG-like structure. And for simplification, we'll just consider that, yeah, analysis at the top depends on analysis at the bottom. And we'll probably use these 4 analyses as a reference throughout. So what can go wrong within analysis and the whole analysis dependence and the whole thing that is just exposed to the transformation as a single unit? Maybe the analysis itself has something wrong with it. Maybe the analysis itself have some bugs. More specifically, the types of bug which arise due to this analysis itself, like the bug that is caused by the implementation of this particular analysis that we're talking about. We are not referring to the bug that it inherits from the analysis that it uses. Now, let's assume a scenario where we have 2 analyses and both of them are correct individually. Both of them are doing what they should be doing. Both of them looks just right. If you see them separately, you are like, yeah, this should be okay. But what we want to focus on, is the interaction between these 2 analyses. How 2 analysis which seems to be perfect, which seems to be correct, may end up giving some unexpected behavior when they're used together, or the way some analysis uses the other analysis. So let's quickly set some terms that will help us to discuss it further. So there are many analyses, and I'm just trying to depict that, yeah, it's a dense net. This analysis depend on that, and it's not simply those 4 analyses. So let's classify analysis as fundamental. Let's consider fundamental analysis are the analysis which do not depend on any other analysis. These are the analysis which we will have at the leaf nodes. Yes, and then we have derived or dependent analysis, the analysis which depends on the result from other analysis. And these are a bit difficult to reason about, because difficult to reason about in terms of correctness, because they depend on other analysis, right? So quickly, let us take a look at how can we test analysis differentially. This is simple, like we would test any other system. So let's consider we have two systems and we want to test them differentially. We have two equivalent system. Two equivalent system can be two compilers, two C, C++ compilers, maybe LLVM, GCC, and then we provide a single test. What we would expect is, we would expect if the two systems are equivalent and if we provide them the same test, then we would expect that in similar situation, they should produce equivalent results, right? Now let's make it a single system. Like we have a single system, and then it does not make sense to run a single test twice on a single system and expect it to be equivalent. But yeah, this can be done. But let's say we have two tests. We have two tests on a single system, and somehow we have to make these two tests equivalent. So what we did is we mutated the first test in a way so that it created another test which is equivalent. So what we have here with us is that we can create mutations which can generate equivalent test cases, and this equivalence is defined by the system. So now we can easily replace this system with analysis, and we can do the similar thing for any analysis. Like we can take an analysis and we can run a test, and we can create an equivalent test using a mutation for that test, and we can check equivalence. But checking equivalence for analysis is not straightforward. We have to define and establish the notion of equivalence for each analysis. Let's say when we are dealing with post-dominated trees, there is a possibility of getting multiple legal post-dominated trees for a single control flow graph. So those things need to be set up, that, yeah, how will you define the equivalence of a particular analysis, right? We just saw that we can use a mutation to mutate a test case into an equivalent test case. So let's talk a bit more about mutation with a simple example. So this mutation is swap true false. It's very simple. It just swaps true and the false branch. So it's a structural mutation in a way that it won't change the structure. Let's say we have a simple CFG with just 4 basic blocks. And if we apply the swap true false mutation on the CFG, what we get is we just get a very a CFG with similar structure, but the labels on the branches are now inverted because of this, right? So we can use a mutation to differentially test an analysis that does not react to it. So let's say we saw swap true and false, and what we saw was that when we use this analysis, the structure remained the same. So we can easily use this mutation to test analysis which are expected to not change when the control flow remains the same. For example, the analysis which work to derive properties out of the control flow, let's say dominated tree, post-dominated tree, and other analysis on the same direction. So these analysis should produce similar result or equivalent result with respect to themselves on such mutation. So we can use this mutation to test such analysis, because we expect that the result won't change. And if it would change, then we know that, yeah, something may be wrong. Suppose we want to test an analysis, we would ideally want a mutation that produces equivalent result for the analysis in question. And this is the basic thing that we are looking here, that we are aiming for, that we want a mutation for which the analysis is inert. And it would be good if we could find a mutation for which the dependent analysis are also the analysis on which the analysis on which the derived analysis depend on are also inert. So at that case, it will help us to reduce all the false positives. Now let us uh, okay. Now, since we have already defined analysis, we have already classified analysis as derived and fundamental. Let us just see what are the sources of bug for what are the sources of bug for this classification, and how can they and how do they differ for both of these? So for in fundamental analysis, the bug can be only caused by itself because these analysis they do not depend on anyone else. So if there is a bug in a fundamental analysis, then it should be coming from itself, right? Yeah. And then the bug in a derived analysis, the analysis which depends on more analysis, it can come from itself or it can come from, let's say, another analysis on which it depends on. And it can come from the interaction that we are focusing here. So to summarize, we can say that for our derived analysis, the bug can be caused by itself, it can be caused by any other analysis it depends on, or it can be caused by the interaction between the analysis. Now, so if you would have noticed, the bugs that are caused by the interaction, the bugs that are caused by the other analysis it depends on, are all the subset of the bug that this analysis will expose. So on some test, let's say on some test, an analysis showed some unexpected result. So this will definitely be counted as unexpected result for that analysis, even though it's coming from some other analysis, even though it's coming from the interaction. So this is a this is a challenge that we will be shortly addressing, that how should we focus on the interaction if the interaction bugs will also be counted as the bug that are in analysis itself, like how can we differentiate? And there is no I would say mechanical there's no like automatic way to do that. We have to do that manually, mechanically, but yeah, let's look into it. So this is not for scale. Uh, let's just consider that the gray part is the bugs that analysis has, and then the blue part is the bug that it has due to the analysis it depends on, and then the orange part is something that we are interested in. It's the area where we denote the bugs that are coming from the interaction. Yeah. So how can we increase our focus to the orange region? Yes. So the first thing that we can do is we can start from bottom, and we can go towards we can go towards the top, increasing the level of trust. So let's say if we start with an analysis that sits on that is at the top, then it's hard for us to and if we find a bug, then it's hard for us to classify it as bug that is caused by itself, that the bug that is caused due to a derived analysis, because there are a lot of there are a lot of analysis on which it depends on, right? But if we start from the bottom and if we say that yeah, these analyses look good, like they looks fine, and yeah, the analysis which uses these analysis, if it has a bug, then yeah, we have already checked these, so it should be coming from that analysis itself, or maybe the interaction. Fundamental analysis are generally the easiest to reason about uh, because they are self-contained. There are less chances of like external or um, maybe other sources of bug which are not easily visible. And it's very wise to say that the post-dominated tree analysis, it kind of work free. Like we can assume that it's a fundamental analysis, like a lot of analysts are using it and everyone is fine with it so far. So and it's backed up by rich theoretical um, formalization. So we can say the same thing for many other fundamental analysis, that these are easier to reason about. And so we have a base source of trust that, yeah, like these analyses are good. So then we can move upward and we can do the same for other analysis, by not just looking at them, but by trying different techniques to find as much as bugs that we can, and so that we can just keep moving upward and we can increase our focus more towards the interaction bugs. Yeah. So as we increase our trust and as we go up, we can say that the bugs due to other analysis should shrink. So this drastic change is not backed up by our data source, but this is just for illustration, that if you are dealing with bugs early on, then it is possible that you may not find them on higher level analysis, and it's also easier to debug and to find, oh, what went wrong, where it went wrong. Yeah. Now let's say as we test the analysis more and more, we are reducing the chances uh, of the bugs that can arise due to implementation, or the bug that can arise due to the analysis itself, again making us more inclined toward our goal, that is to reach towards the analysis, reach towards the bug that are at the interaction of the analysis. Now, if we choose mutation such that the mutation are itself inner to the analysis and the analysis on which this analysis depends on, right? So if we try to find mutations and use them to differentially test this analysis, then since this analysis and all the analysis that this analysis depend on are inner to it, we are increasing the chance of finding something that should be or maybe an interaction bug. Yeah. So these assumptions so far has turned, I would say, decently okay. And yes, and I have an example to demonstrate all what I have said so far. And it's region info analysis in LLVM. So region info analysis, it depends on three analysis, on which dominance, frontier analysis, it depends on dominated tree as well. So we assume that, yeah, that the post-dominated tree, dominated tree, and dominance frontier are fine. Like we gave them, we have some. We have some trust on them. We are like, yeah, these are fine. And if we wanted to, we would have tested them. But since they are very popular and used widely, it's wise to say that, yeah, they are okay. Then we have a simple test case, just 5 basic blocks, and we'll use the mutation swap true false that we discussed before. So if we apply the mutation swap true false at basic block 1, this is the control flow that we get. It's totally same, just we have flipped the true and false label for branch at the end of basic block first, right? And what we are talking here is the region info pass, which region info is a structural. It tries to drive something from CFG, and it should remain same if the CFG looks same. So this is the mutated test case. Let's just quickly go through what region is. I see that I don't have much time, but yeah, let's just quickly see what region is. And yes, so region is a connected subgraph that exactly have two connection to the remaining graph. So we can say this is a this is a region considering 1 and 9 to be the imaginary two connections. We can say this is a region considering 2 and 9 as the entry and the exit, or the two connection to the remaining graph. So this is what region is for basic blocks. These 1, 2, 3, 4, 5, 6, 7, 8, 9 are basic blocks. So what happened to the test cases that we mutated was that for one test case, we were able to find a region. And for the other test case, we missed a region, right? So you will say how bad it is to miss our region. So to tease a bit, we have a region pass in the legacy pass manager, right? So the other question that would come to you, that was it really an interaction bug? Like we were talking about finding interaction bug for so long, like was it really an interaction bug? So as I said, that we cannot decide that automatically. If we have to, like we have to do that manually. We have to sit down and we have to see was it. But if we followed all the if we followed like right things, then it increases our chances of finding an interaction bug. Like things have become so mature in LLVM that these are just maybe just rare corner cases, but yeah, they exist. So in the next few slides, I would have talked about how region info analysis pass work, and it seems like I'm short of time. Let me skip this part, but this will be available in the slides that will be uploaded. Yeah, and this is just a walkthrough about what exactly happens, so, and what is the exact difference between the two. So the region info analysis pass misses that. But I'll try to highlight few things. So the one thing that I want to highlight is yeah. So here I have combined both of the test cases, the test case and the mutated one. And this is the result for dominated tree. And for both of the test cases, it's the same. The thing which changed was the post-dominated tree, and for two similar structured test cases, we got two different but legal post-dominated trees, right? And the way region info pass uses post-dominated trees, that is the reason it missed a region. Yeah. So in the next few slides, I would be walking through that what happened and what like how it missed a region for one test case, and how it was able to figure out a region for the other one. Okay, but let me reach to a conclusion. So what went wrong? So the region analysis did the right thing at its end. So there's no doubt that the region analysis is not working correct or something like that. So it did the right thing. If you see the region pass, it did the best thing that it should do. And if you see the post dominator analysis as well, it also did the right thing. Yeah, but it was definitely it was definitely their interaction which led to this unexpected behavior. So as I said, how bad it was. So how bad is missing a region was, and I teased you that we have a region pass. We also have a pass called structurized CFG, which uses region info. I guess it's a region pass, and it crashes when it sees the CFG, which we are not able to detect region. So it's pretty bad. Like the compiler crashes. I also tried to grab things, and I could find that Poly uses scoop info analysis, which depends on region info, and scoop info analysis is used by other passes. Though I don't have much idea about Poly and how severe it is or bad it is, but yeah. So let me just conclude here so that we can just have some quick questions. Compilers are complex, no doubt in that, and it's okay if we are missing some rare test cases. But a key takeaway could be that when we write an analysis, we should be aware about the corner cases of the analysis that we are using. Yeah. And we should definitely come up with new techniques to test the interaction between different analyses. So thank you. And yes, let's have questions quickly.
Awesome. Thank you, Rishabh, for presenting. If you have any questions from the audience, please, if you raise the hand, then we can allow you to speak, or you can type the question in the chat, whichever way you prefer.
Well, we give people time to type a question or come up with one. So you use this mutation approach. Did you use the upstream mutation capabilities, or do you build your own?
Oh, no, I didn't use infrastructure that is upstream for this swap. Swap true and false. I just wrote a small transformation path.
Okay, so and do you have other mutations or just the true and false one?
Oh no, I don't have any, but I definitely I haven't got the time to think about it, but I want to extend it a bit and come up with some more results. Yeah.
Right. That's cool. We're trying to do some Google Summer of Code work in fuzzing passes. Maybe that is something that you might want to take a look at.
Oh wow, yeah, this definitely led my interest to fuzzing. Like after this, I sort of became a fan of fuzzing techniques, and I read quite a few things about that. Yes, so I definitely would like to have a look. That sounds cool.
There was a work by Mandeep a few years ago from Qualcomm. What he did was like he just reversed the order of iteration, and he found like so many bugs in LLVM. So it's like a poor man fuzzing, but that simple thing itself. And I think what the example you shared, like changing true to false, is like a similar like artifact, right? Like changing the order we visit the nodes. I guess that's why it found a different post-dominated tree, right?
Yes. Yeah,
there's probably more bugs there.
Yeah, and I guess it all at least here it all boiled down to the post-dominated tree. Yeah, if it was same, then we won't be seeing any of this. Yes.
Yeah. Okay.
Which basically begs the question: can we make it canonical, such that we don't these artifacts?
I guess we cannot, because so it's a trade-off between whatever optimized implementation we have for post-dominated tree and how much we care about such artifacts.
I mean, like your backend crashes if the post-dominated is the wrong one. So I would argue you care a lot. So Michael posted a comment about the poly thing. Poly, I mean, it depends on how you look at it. If the region is not detected, poly will just ignore the code, so it will not run on it. So it's harmless in a way, but you miss out.
Yeah, I was not aware of this, but yeah, this is a nice info for me. But as you said, yeah, the crashing compilers, it's definitely severe. But I guess crashing the crash of a compiler for a particular backend, a particular target, I don't think I don't feel that thing is able to drive the motivation to change all this. Like definitely I want to change all this and improve this, and even I spent some time thinking about that what we can do which is less disruptive, but I was not able to come up with something like that.
Okay, but I really like that, and I think there's a lot of interesting follow-up work to do on that. And as Aditya said, prior works there found a lot of bugs, and I think this can really find quite some more, and not only bugs, but also these kind of artifacts that you really want to avoid.
Yeah.
Okay. So let's move on to our next speaker. Thank you again for your talk.
Okay.
Great.
Thank you so much. Yeah. So I guess I'll just stop sharing my screen, right?
Yes.
Oh, okay. Thank you. Yeah.
Perfect. We see the screen, and I think you're good to go.
Okay. Perfect. Good afternoon, everyone. I'm Gökçen Kestor from Pacific Northwest National Laboratory. And today I will talk about our compiler, COMET, domain-specific compilation in multi-level IR. So we have been, because of the increased complexity of heterogeneous system, we have been seeing a lot of domain-specific languages in the area, especially as AI became predominant and targeting different heterogeneous systems. So, but here on the right-hand side, what we can see, there are many domain-specific languages or frameworks, and underneath we are seeing a lot of specialized architectures. So when we think about the one-to-one mapping from one domain-specific language to a heterogeneous system, so this is causing a lot of barriers across the domains and causing also lack of interoperability across compilers. And when we think about the different domains, for example, Power Grid and NWCAM, this causes the difficulties cross-disciplinary collaboration. And so because of that, we developed a COMET compiler. COMET compiler targets different application domains and targeting heterogeneous system. So in a nutshell, what is COMET? COMET is a compiler infrastructure, come with the DSL as well. On the right-hand side, we can see the compilation framework, compilation pipeline of the COMET compiler. And we have a DSL, is a targeting tensor algebra operation for dense and sparse computation. And COMET compiler based on MLIR and does several multi-level code optimizations. And its goal is to generate efficient code targeting heterogeneous system for sparse and dense computation. So during this presentation, I will go to the details of the two pipeline for the dense and sparse, and I will show some experimental results that what is the performance of the generated code. So as I say, I think it's not, everyone is aware of MLIR, and we are also building our compiler on top of the MLIR infrastructure. So at the beginning, I mentioned that COMET is a domain-specific compiler. So we are looking at computational chemistry as a domain. And in this case, NWCAM is one of the main application at PNNL, and which is a computational chemistry suite. And in this application, dense tensor contraction operations are the ones that span significant fraction of the supercomputing time. And what is a tensor contraction? Tensor contraction are the higher dimensional analogs of matrix multiplication. For example, if we want to perform an expression similar to this as a tensor contraction, we can write our tensor contraction in a loop form. But there are some problems with this one, because writing a tensor contraction in this form, it will cause a poor performance because of the data locality. And there is an enormous space of the loop permutation, how we will put actually, what is the optimal loop permutation and tiling looking at this tensor contraction. So one other side that the domain scientists, chemists, they would like to write their application by using a very high level programming languages. So in this case, they don't want to write their application using an loop form or worried about how to optimize, considering the architecture also. So what we did, we developed a DSL and targeting sparse and dense tensor algebra operation. So this is how our DSL looks like. And in this case, what we have two types of index labels to express the static and dynamic index labels. Dynamic index labels mainly for the sparse computation. And we declare the tensor, defining their types. And also in the tensor declaration, we can specify the tensor storage format. So in our compiler, we support most common sparse tensor operations and the dense. So this is how in the language that programmer define their storage format. Then we have some utility functions to be able to read the input file and initialize them. And finally, this is how the user programmer sees that how they can use the Einstein notation to express their tensor operations. So, and by looking at this DSL, the first thing that we are lowering our code to our tensor algebra dialect. So there is almost one-to-one mapping between language to the tensor algebra dialect. For example, here we see that how index labels express in the IR and the tensor declarations as well. Here we can see that the format also expressed in this way, and initialization of the tensor and the ta.tc tensor operation. So now going to the details of the how do we optimize our code considering the dense tensor contractions. So now from language to tensor algebra dialect, I showed how we go from TAAST to the tensor algebra dialect, and the down part actually focusing on how we can optimize this code. So the first thing we are doing, we are reformulating the tensor contraction operation by using the transpose-gem transpose approach. Then in the lowering part, we have two types of code optimizations, high-level code optimizations and the low-level code optimizations. So let's look at what is transpose-gem transpose means. So this is a very common approach using for the tensor contraction and the NWCAM as well. And the reason that if we reformulate the tensor contraction operation through this way, we can leverage optimized gem kernels. And how we can do that? So let's assume that we have this tensor contraction operation. And the first thing we will do is flattening the tensor to matrices. For example, here we can see that our tensor in this way, we are reshaping the tensor, flattening, and looks like is a two-dimensional matrix. And is the same for the second operand is the tensor B, and we perform the gem operation. And if it is necessary, we can retranspose back the output tensor in a way that what we need at that. So looking at this, how we represent this TTCG in our IR. So on the left-hand side, we can see that this is our tensor contraction operation. And here we are using the indexing map represented here, how to find the optimal index permutation to perform the TTCG. So in this example is very simple one and is showing us we transpose the first tensor and convert into two-dimensional for the second tensor as well. And then there is some reshape operation in the middle to fit the, we are moving from 3-dimension to 2-dimension. This is our, in the linear algebra, linear algebra dialect, we have the gem operation and the final transpose for the final output. So after this formulation, we also leverage several high-level optimizations. So since we are targeting NWCAM as an application, in NWCAM, there's a chain of tensor contraction operations. So in this case, we look at how we can optimize these operations, because it is important to pick up choose the optimal ordering among the tensor contraction for the performance result. For example, I have this chain of tensor contraction operation, and I want to follow the naive approach that putting the parentheses. So first A multiplied by B, the output will be multiplied by C. And here we can see the complexity of this operation. But the compiler can make a better decision reordering this operation similar to this one. We swap B and C, and we perform A multiplied by C, then multiplied by B. So we can see that this is reducing the cost of the operation significantly. Also, what we did, we use a heuristic to minimize the transpose cost. Means that we are in the compiler, we have a heuristic pick out the optimal index permutation to reduce the number of transpose operation while picking up what is the index permutation should be. And going to low-level optimization, after the TTCG, we have two main operations in our compiler, transpose and jump. So we focus how we can actually optimize these operations. For the transpose, we use a heuristic comes from the library HPTT to pick up the loop ordering when we lower the transpose operation. And then for the jump, we leverage the state of the work coming from the Bliss libraries, how we can do the tiling to increase the data locality and to be able to use the caches better. Okay, so this was so far I talk about how our dense compilation pipeline working. Then after that, we move to sparse computation. So the reason that we would like to now still work in progress, but we would like to focus on the graph analytics applications as well. So looking at what is a sparse computation, and sparse computation actually widely using many applications, scientific computing and data analytics and even machine learning as well. And for the sparse computation, there are different storage formats because we don't want to store the sparse matrices in the dense format because of the storage requirement. And there is no need to compute the unnecessary redundant computation, considering that a lot of there are non-zeros. But there are a lot of challenges with the sparse computations. The main one is writing the sparse kernels is quite hard, considering we have many different storage formats. And in terms of computational challenges is that there are a lot of irregular accesses in the sparse computation, and we don't have a good temporal locality and spatial locality. So there are libraries comes out with some solution for the optimize some of the sparse kernels. However, considering the combination of the sparse storage formats and the different tensor expression and the underlying heterogeneous target architecture, sparse is difficult to think about. Sparse libraries can address all the challenges we talk about. So for our case, we want to rely on sparse compilers. Sparse compilers will simplify the development of sparse kernel, automatically generating the code and only looking at what is the sparse property of this tensor. Is it dense or sparse? So going to the details of the sparse compilation pipeline, so I will talk about more details on the right-hand side of the compilation pipeline. So here, for this work, we define an internal storage format to be able to target important storage, sparse storage format. And in our compiler, we have a sparse data type, and we are using attribute per tensor dimension, again, connecting with how we are supporting different storage format. And the compiler itself automatically generates the sparse kernel based on the expression and their sparsity. And one important thing that our compiler can generate sparse output. It doesn't need to be every time to dense. And we have some input-dependent optimizations in the compiler. The compiler is leveraging. At the end of my talk, I will talk about the performance numbers with this optimization. So, as I mentioned before, there are a lot of sparse formats in the literature. And the reason being that different storage formats represent different code structure and the performance. But implementing in the compiler different compilation passes per format is difficult. It's difficult to provide the maintenance. So what we did, we look at the literature and we leveraged the TACO work, and then we used a similar approach representing the sparsity of each dimension. So we define 4 attributes in our compiler. So dense, compressed unique, compressed non-unique, and singleton. So each of them means different things. For example, if it is the dimension is dense, in our internal storage format, we can use only the size of the matrix or tensor. And if they are non-unique, we have to we need to store all the non-zero coordinates in one array, and then just looking at the start and end position of the coordinates. Through these 4 attributes, currently we can support important storage format, including coordinate format, CSR, double CSR, mode generic format, or the CSF for tensors. So briefly look at how actually these attributes represented and how the data looks like our internal storage format. For example, assume that this is our matrix in the sparse matrix. We want to store in the CSR format. The user is saying this is a CSR because we want to generate the CSR code structure. And this is how the data looks like in our internal storage format. The first dimension is dense. The second dimension is compressed unique. As I said before, for the dense, we are storing the size of the row. In this case, is 5. And compressed unique, it is similar to CSR format. So we have the coordinate position and coordinate, and this is looking at how the column can be represented similar to CSR. And we can see that if we go to coordinate format or double CSR, the data is stored in a different way in our internal storage format. So just to show how our compiler automatically generate codes for the SPM, sparse matrix, dense matrix multiplication. So here what we can see in the tensor contraction operation in the IR, the user in the language level, user says, I want this data is in coordinate format. We lower this information to an intermediate representation, and our compiler can generate this code. So this code is represented in the structure control flow dialect in MLIR. So when we move to another way of representing the same operation in the CSR, what we can see, automatically generated code has differences and follows how the user would like to generate the code based on the format. And finally, in our compiler, we leverage a sparse tensor reordering optimization to enhance the data locality. And we leverage the state-of-the-art state tensor reordering algorithm called LexiOrder. And this algorithm is using the double lexical ordering algorithm and mainly cluster the non-zero elements on diagonal and top left. So moving to results, at that here, I am showing you the performance of automatically generated code through COMET and comparing with the state-of-the-art implementation. So for the state-of-the-art implementation, we use optimized libraries. For example, for GEM, we are using the Bliss library. For transpose, we are using the HBTT library. So what we can see, the performance of the automatically generated code by COMET for some cases actually 2x speed up, provides 2x speed up. Also, I forgot to mention, there are the tensor contraction operations we can see on the x-axis coming from the different application domain. And on average, we can see that our compiler provides 20% speed up across different tensor contraction operations. And the next analysis we provided here, we look at 118 dense tensor contraction operations coming from the LWCAM methods. They are mainly coupled cluster T1 and coupled cluster T2 methods. So these methods include a chain of tensor contraction operations consist of 3 and 4 operands. So here what we can see with the optimization that I mentioned before for the multi-chain optimization, we can provide for some cases almost 24x speed up. Moving to the sparse performance of the sparse kernels, we compared automatically generated code by our compiler with the TACO. TACO is the state-of-the-art tensor algebra compiler, is commonly used in the area. So here we look at the performance of a COMET compiler with almost 2,800 matrices coming from the Swiss sparse collection. And we can see that this operation for the sparse matrix vector multiplication on the right-hand side, we can see the performance of sparse matrix, dense matrix multiplication. And on average, we are providing like for the SPMM, 2x speed up to 6x. And the reason being that we look at the generated LLVM IR and it reveals that COMET generated code leverage better vectorization and the loop unrolling as compared to TACO code. So here for the parallel execution, we lower our code to async dialect in the MLIR and compared with the performance again TACO by using 24 parallel threads. And here we can see that very interesting part, especially for the SPMV, there are some cases that COMET compiler performs like over 190 per X speed up as compared to TACO. And the reason we look at and we investigated and we found that it looks like the overhead of the OpenMP runtime is noticeable as compared to async runtime using MLIR, especially looking at the small matrices. And this affects actually, it's a little going down when we increase the number of non-zeros in the matrix. And here, that also I wanted to show the results of the optimization I mentioned related to data reordering. And in this graph, looking at the parallel SPMV and parallel SPMM operations, and we compared the performance of COMET with and without data ordering. And what we can see, some cases, we have very good performance. And we can see here a 7x performance improvement with the data ordering. But some cases, the performance degradation is significant. And what we did, we look at these particular cases that we have 7x performance improvement with the data reordering and on the other hand, 9x slowdown. So in this figure, we can see the visualization of the matrices before ordering and after reordering. And we can see that actually it explains why if every non-zero elements is clustered on diagonal and in the balanced way, we are having a very good performance. But the non-zero elements is clustered on the top side of the matrix, there is a load imbalance. This is the reason that we see this performance degradation. And just to conclude, COMET compiler introduced a domain-specific language for the sparse and dense tensor algebra operations, targeting computational chemistry in graph analytics. And our compiler, based on MLIR, automatically generating code for sparse and dense computation with several optimization techniques. So far we see good results with both cases, and we are investigating some of the performance degradation and like how we can improve them. So we are working on the paperwork, how we can release the COMET compiler. Hopefully it will be open source in the near future. And thank you so much. Thank you so much for attending the talk, and I'm happy to take any questions you might have.
Great. Thank you. Do we have questions from the audience?
Okay, so I'm trying to see how can I see the questions actually.
We don't have any so far.
Okay.
I will let you know. I have the chat open. Let me ask one. So you had this graph where the OpenMP runtime overhead of Taco was significant. It kind of looked like all of the tests for Taco roughly took the same kind of amount of minimal time. Is that the time it takes to initialize the OpenMP runtime?
So I think it's a good question. So I don't know the exact answer. Is the part that we are still investigating,
okay.
And it could be the reason because looking at the small number of non-zeros, the computation looks very small in the kernel, and there is a significant computation execution time comes from somewhere else. So it could be maybe initialization of the OpenMP runtime or something else.
Okay, that makes sense. And you said the generated IR from COMET is vectorized better. Do you happen to know why?
And not really. Actually, I had several conversations with some folks from Google as well, and there is no clear answer like why it's happening. And here, actually, the conclusion that we can come, the IR, LLVM IR dialect generated through COMET enables better optimization when we move to the LLVM IR. So this is, again, like we are collaborating with the Google to figure it out what could be the reason.
Okay, that sounds good.
That's just the numbers. For example, in our paper we mentioned, now I don't remember the exactly, but is using generated LLVM IR comes from the different COMET and TACO. They use different parameters for the vectorization parameter and the loop unrolling. And even though they use the same level of optimization, O3.
Right, but yeah, it will be good to understand why this is. It's kind of artifacts that sometimes have a huge impact, and if we don't understand why this happens, any future change might actually undo the whole improvement. That is always a little.
Yes, scary. I agree, and as we talked before, I'm happy to share the generated LLVM IR coming from the two compilers that I will be happy to also to have a clearer understanding on this.
That seems like a reasonable approach to take like 2 small examples.
Yes, perfect. I think we can do that.
And you said you're hoping to open source COMET, right? It's not open source right now.
Not yet, because for from the lab, I need to complete some paperwork. But if anyone is interested, that I can share the repo and we can collaborate together. Currently, it's not open because of the intellectual property coming from the lab itself. But I am happy to share with individuals, especially like, as I mentioned, this LLVM generated LLVM IR, how to do that. I can do that. I don't see any problem for this.
Okay, that sounds great. Yeah, we're certainly looking forward to seeing this in the open and people playing around with it and testing it out.
Yeah, it's great. Also, I'm looking forward to that.
Okay, thanks again for your talk. Really nice. We'll go to our next.
Perfect. Thank you so much again. And I know I'm stop sharing my screen.
Yes, perfect. Stefanos, you're up next, right?
Yeah, it seems so. Hi, everybody. Hi, Johannes. So I'm just sharing my screen, right?
Yes.
Okay, cool. All right. Can everybody see?
Yes.
Okay, cool. So welcome, everybody. In this presentation, we're going to discuss some of the latest advancements in automatic vectorization research. The goal here is pretty much to let the community know about some of the latest things that have been done, because it seems to me that vectorization has stayed in really old stuff in most production compilers. And yeah, I guess that can motivate some future work. Okay, so here we have some code. You're probably familiar with some variation in this code. So what it does is we have this outer I loop and this inner j loop. And we can see that we access the array as ji, which means that first we pick a column with I, and then looping through j, we loop through this column. Okay, and what we do with the elements of this column is we just accumulate them, and then we store the sum in an array. So visually, that looks like, well, if we assume that this is the memory layout of arrays A and B, and so these are the rows of A and these are the columns of A. What we do is we pick an I and then we just loop through J, accumulating the elements of a column, storing the sum, going to the next iteration, so on and so forth. Okay, now let's say that you want to vectorize this code. Now, reasons to vectorize the code. Well, for one, you might be like, okay, vectorization would be good. Like, I would like vectorization, it would improve my performance and all that. But there are cases, like for example, in vector engines, like the SX Aurora that is being produced by the company I work on, NFC, I mean, for such vector engines, vectorization is absolutely non-optional. So you absolutely have to do vectorization to get advantage of them. Now, the problem is, unfortunately, that in most production compilers, the only option that you have is innermost loop vectorization. And I know that there's this straight line code vectorizer or SLP vectorizer. This is kind of really somewhat besides the point here. I'm mostly talking about loops. And unfortunately, the only option we usually have is innermost loop vectorization. So that's what we're going to do here. In this case, this innermost loop is this J loop right there. And the way this looks like is basically we still pick an I. This is just the same memory space, but bigger. We pick an I, but now instead of doing one iteration at a time in the J loop, we do 4 of them. So it looks like that. We're not visiting one element every time, we're just visiting 4 of them at the same time. So then another 4 of them, then we pick an XI and we visit another 4 of them, and we just continue. Sorry, oh, okay, yeah, I guess the chat. Okay, cool. And so we're just continuing. And the thing is, we have this vectorization, and we might be like, okay, I'm doing the same amount of work, like I'm doing steps of 4, right? So I'm doing the same amount of 4 times the amount of work in the same amount of time. So that seems great. I should have performance improvements, right? And unfortunately, the benchmarks don't really show that. And the reason for that is because we have cache misses everywhere. Okay, so pretty much in every access here, we're going to have a cache miss. And the reason that this happens can be also inspected in the serial code, the original code. It doesn't really have to do with vectorization. It's just something that is sort of preserved when we do vectorization. So, here, back in the serial code, in every axis, we have a miss, and that continues to the next column and so on. Okay, but why are there misses? Well, going back to the memory space, what I want to show you is how are 2D matrices usually stored in memory. And when I say usually, I mean in most programming languages. Now, memory, physical memory, is linear. Okay, there's no 2D memory. And so basically, we have to store something that is fundamentally 2-dimensional in something that is 1-dimensional. So we somehow have to sort of cheat. Okay, and the way this usually happens is we store the matrix in row order. So that basically means that we, here we have colored the first 3 rows. And so in the linear space, they're stored like, okay, first all the elements of 1 row, then all the elements of the 2nd row, then all the elements of the 3rd row, and so on and so forth. Okay, now let's say that we're going to do an access in an element. Let's say that we're going to access this element right here. Now what happens is really that going into memory to grab an element is really slow, okay? So what we try to do to help with that is to say, hey, since you go all the way to the memory to get an element, don't bring 1, just bring more of it, okay? And let's say that we can bring 4 elements along with us instead of just 1. Now the next question is, what elements do you bring? And this is something that happens automatically, and processors try to take advantage of something called spatial locality. So they try to predict what are going to be the next elements that are going to be used. Because if you bring those elements along with you and you just use them right after this element that we just accessing, then we won't have to go to main memory again. And so processors predict that the next elements that you're going to use are going to be the elements that are near the element that you access in the linear space. This is very important. The processor doesn't know about this 2D space. So in the linear space, the elements that are near this element that we're accessing are these 3 elements right there. So 1 element that we're accessing plus 3, equals 4. Now the problem is that if we bring this back to the 2-dimensional space, actually none of these 3 elements is going to be an element that we're going to use next, because the next element that we're going to use is going to be this element right there. And although it looks very close to the element in the 2D space, in the linear space, especially as rows get bigger, they're very far away. Okay, so we're probably going to have a cache miss. And that trend is going to continue, because when we access that, we're going to bring this other 2 elements, and none of this is going to be used next, because the next element is going to be the first yellow element right there. Okay, so what if we could do outer loop vectorization? Would that be beneficial in some kind of way? Well, first of all, let's try to understand what is really outer loop vectorization. It's basically the act of vectorizing a loop that is non-innermost. So it has at least 1 nested loop inside. For example, in this case, it's the I loop, okay, because it has a J loop inside. Now, the way we're doing outer loop vectorization is pretty similar to how we're doing, conceptually. It's pretty similar to how we're doing the innermost loop vectorization, but there's a slight difference that I want to bring the focus on. Okay, so normal loop vectorization, we just go, say, in steps of 4, let's say that our vectorization factor is 4. And then usually what we're doing is for rev operation, we're just having 4 pieces of data, and we're assuming that we're going to do all of them at once. We're going to do the operation all data at once. So here, just want to bring an attention that it happens that this data that we have, this 0 that we start, is independent of the iteration that we're. So this is why you see 4 copies of 0. This is not generally the case. We don't just copy the data that is initially there in the serial version. So for example, if that was I, in which case it is dependent on the iteration that we're at, then when we're doing the quadruple, we have to say I plus 1, I plus 2, I plus 3. So it's dependent on the iteration. Anyway, so back to our story. Of course, I guess it makes sense here that basically outer loop vectorization, we're going to see that in a little bit visually. Is really in the original version, we just loop through a column and we sum the elements. Now we're going to loop 4 columns at the same time. And so it makes sense that you need 4 accumulators. And that's all great. But now the thing here is we stumbled upon a loop. And that's kind of not something that we've seen in our most vectorization. So what do we do in that? So we're going to sidetrack this for a little bit. And what we're going to do is we're going to take the sum here. We're going to say this is 2. And the reason, let's pretend it's 2. And the reason we're going to do that is because now we can unroll the loop. And because we can unroll the loop, we can apply the same techniques that we apply for normal or innermost loop vectorization. So, you know, we're going to have 4 J0s, 4 loads. We're going to have 4 accumulations. And using the same logic, we're going to do that for the other quote unquote iteration. Okay, and we have reached this place. But I want to bring the focus on these 2 lines here, okay? Because we see that we have 4 J0s and 4 J1s. And what I want to ask is, do we really need 4 of them? Do we really need 4 copies of each one? And so if you pay attention, we have 4 J0s, but they all have the same value and they don't change their value. So all J0s start at the same value, and they all stay as the same value. And the same is for the 4 J1s. So it makes sense that we don't really need 4 of them, right? We can just use 1 of it. Now, it's important to understand that we really need 4 loads here, and we really need 4 accumulators because, of course, the J0Y element is not necessarily the same as J0Y plus 1. Okay, it's only for these J's that they stay the same because we don't change them somehow. And so using the same logic, we don't need 4 J1s. And in general, that is going to be true for any, you know, we picked M to be 2, but for whatever M is going to be the same. We don't need 4 copies of sort of the induction variable. We just need 1. So we can bring this back to just normal loop, right? So we have this loop here, and the body is vectorized, but the induction variable has remained scalar. And just want to show this transition because a lot of times when I was introduced to outer loop vectorization, is you see this code having quadruples everywhere, and you just question, hey, you are making 4 copies of everything. Why is this loop staying intact? And I just want to show that there is a reason that this J doesn't have 4 copies, just has only 1. Okay, and of course, using the same logic, we're going to have 4 copies of the stores and so on and so forth. Okay, now, the way this looks visually is basically now, instead of picking 1 eye, you pick 4 of them. And what you do is you just, as I said, you're just looping through 4 columns at the same time. So for J0, instead of visiting 1 element, you're visiting 4 of them. So 4, accumulate the next 4, accumulate the next 4, accumulate. Oh, sorry. Okay, didn't mean to do that. Accumulate the next 4. And what we see here is that this is different from the innermost loop vectorization. Because yes, every time we access the 4 elements of a row, we have a miss. But at least now we actually do 4 times the work at the same amount of time. So yes, we do have a miss in every axis here, but at least we're doing 4 times the work, okay? Another way to see how this looks visually is maybe to compare it with outer loop parallelization. So in outer loop parallelization, let's say you had 4 threads. You would start each thread, you would pick an eye, so to speak. But the threads would not be coordinated at all. They would just start, and at some point, maybe some of them finishes first, and it picks some other column. You know, they're completely uncoordinated. In vectorization, happens what we call lockstep. Okay, so it's thread. Conceptually, it's like doing coordinated steps with each other step. So it's thread does 1 step, then they all move to the next step, then they all move to the next step. Of course, this is just a conceptual idea. It's not enforced in some way in hardware. We don't put any kind of barrier or something like that. Okay. Now, this outer loop vectorization thing becomes a little bit more interesting when we start having conditions. So here we have the same code that we had before with just one minor difference. And the difference is that now we're not accumulating every element, we're accumulating conditionless. So we pick some of the elements. And the condition is brought from this array right there. Okay, so for example, if we bring that back the visualization, we're just summing some elements, but we don't pick all of the column. We just pick some of the elements of the column, and we store the sum. Yeah, sure. Okay. So why is this interesting? I'm going to introduce a small definition. I don't really like text in slides, but this is important. So we're going to say that a uniform value is characterized in relation to a loop, and is one that does not vary because of this loop. Now, this because of this loop is going to become very important because the value may vary otherwise, but if it does not vary because of the loop, it's uniform in relation to this loop. And we're going to see examples of that. Just want to say that anything that is not uniform, you might see it as divergent or maybe varying. Okay, now to the examples. First, innermost loops. Uniformity in innermost loops is really pretty simple. It's the same as loop invariance. Okay, so if you have an innermost loop, anything that's loop invariant is uniform, and anything that is uniform is loop invariant. So for example, here V is loop invariant and is also uniform. You can bring it out of the loop. Now, in general, I want you to think that loop invariance is a stronger condition than uniformity. If something is loop invariant, then by definition, it does not vary because of the loop that we're interested in. So it is also uniform in this loop. But the inverse does not necessarily hold. Okay, and this is what I want to show you. And this is where kind of outer loop vectorization stuff becomes interesting. So back to the original code that we had here. Let's concentrate on this condition right there. And let's try to characterize it in relation to the L loop. I'm going to characterize the uniformity and the loop invariance. So we can see that P changes. Okay, it doesn't have a constant value, it doesn't have even a predictable value. But the important thing is it does not really change because of the I loop. It changes because of the J loop, right? So if we pick a specific J, let's say J is equal to 0, and we start varying I, P is not going to change. It's not impacted by the I loop. It's impacted by the J loop. So it is uniform in the I loop, but this is a loop invariant. And of course, we can see that this is not loop invariant. We can't, for example, take P and move it outside of the I loop, okay? And hopefully that shows us that uniformity is a different concept than loop invariant. It's actually a weaker condition. And this is important because even having this condition we don't need loop invariance. We need uniformity to have something very powerful. And this powerful thing that we can have when we have uniformity is that we can vectorize without vectorizing the condition. So you might know that when you vectorize the condition, you have to do predication, or you might have heard it as if conversion. So basically you have to create a mask, and then in the vectorized version, enable some of the lanes depending on the mask. It becomes very complicated, but it's not as efficient as having a scalar condition. But if we're vectorizing a loop and the condition is uniform in this loop, we can leave it scalar. So for example, here we have the vectorized version, and it doesn't really matter. The code's a lot of code. It doesn't really matter. But what matters is that this P has stayed scalar. And again, the intuition behind that is that in vectorization, you're doing multiple iterations at once. So in this case, we're doing multiple iterations of the I loop. Well, because P is only impacted by the J loop. So again, if you pick a specific J and you vary I, it doesn't change. That means that, let's say for J is equal to 0, P is going to have the same value for every I. For J is equal to 1, P is going to have the same value for every value of I. So you don't really need to have 4 copies of that. Again, visually, the way this looks like is, say P is true, it's true for every, if this goes through J and this goes through I should have labeled that, by the way. Well, for a specific J, either you take all the elements, or maybe you take none of the elements, or you take all the elements, that's okay, but you never have a situation that looks like this, where for a specific J, let's say J is equal to 0, you vary I and you have P changing. That never happens because it is uniform. And so the last thing I want to talk about in outer loop vectorization is I just want to give a shout out to the region vectorizer. It's a vectorization framework built on top of LLVM, and it can vectorize all sorts of stuff. Basically, it is kind of let's say the same as this ISPC, but for control flow graphs. You can pretty much vectorize anything that is reducible. So inner, outer loops, whole functions. And I think that is important in the regional vectorizers. There's some work in outer loop vectorization that can vectorize loops, but it has some kind of a limit in the loopness depth. So for example, doubliness loops. The regional vectorizer has none of such limitations. Okay, so next topic is recursive tree traversal vectorization. So I think this now goes more into research territory. It kind of becomes a little bit more ambitious, because yes, loop vectorization and uniforms and all that. I mean, hopefully that was interesting. But it's still in affine loopness. It's still in dense loopness. Recursive tree traversal vectorization, it just doesn't. It seems like an oxymoron. How would that happen? So let's see how could that happen. So let's say we have a tree. It's a binary tree. It's not a binary search tree. It's not supposed to be one. And I'm just saying that because we're going to do some traversals on that tree. Don't worry if they don't look like binary traversals. It doesn't really matter. And what I have done with this tree is we have this tree above. And on the bottom, there's a table. And on the horizontal axis, there are the nodes of the tree. And in the vertical axis, there are some traversals that we're going to do in the tree. And what we're going to do is we're going to just label for every traversal that we're going to do what nodes does it visit. So let's say we start at the traversal A and starts at node 1, the root, goes to the left subtree at node 2. And let's say it likes the left subtree, so it visits the whole left subtree, blah, blah, blah. Just doesn't find what it wants, goes to the right subtree and says, oh, here we are. Okay, in 3, I'm just stopping here. So then we're starting a new traversal. This starts at the root, goes to the left, doesn't like that, goes to the right and visits the whole right subtree. And then we have a bunch of traversals, okay? Now, the important thing here is why is traversal vectorization difficult? Or so to speak, why it is not easy to make it efficient? Let's suppose that what we're doing is we're just trying to vectorize traversals A and B, trying to execute them at the same time, okay, with a vectorization factor of 2. Okay, what are we going to do? Well, we're going to start here. Both traversals visit node 1. And that's great because we can load the data of node 1. So one piece of data, we're going to do one load, but we're going to do 2 steps at the same time. So that's great. We're efficient up to now. Then both visit node 2. Great. Same again. We're loading one piece of data to do 2 steps, right? So in the original code, in the original execution, we would do 2 loads, one for each traversal. But the problems arise when these 2 traversals diverge. So now one traversal visits node 4, the other traversal visits node 3, and that's really no good. Because now you have to load 2 pieces of data. They're in completely other places in memory. And you basically, while you're doing all that, you also are using vectorized instructions, which are not so easy to handle in the pipeline as scalar instructions. So basically, if your traversals diverge, you have a problem. And it's difficult to vectorize traversals because it's really difficult to predict if traversals are going to diverge. Ideally, so what you would like is your traversals to look something like that. So traversal A is seen, they visit the same nodes. They don't have to visit the same exact nodes. I mean, they have to be similar to sort of visit the same nodes. Because then you could just vectorize it as we just saw. But the thing is, how do you predict whether some traversals are going to visit sort of the same nodes? So one technique that has been tried is the following. It works something like that. What we're going to do is we're going to start a traversal. When we're starting the program, we're going to start a traversal, no vectorization yet. And what we're going to do is we're going to say, hey, every 4 nodes, I'm going to write down in what node I'm at. So I start the traversal A, and after 4 nodes, I'm in node 8, okay? And I'm noting that down. Then after 4 nodes, I'm in node 11. I'm noting that down too. And then no more 4 nodes for traversal A, so I'm just finishing. Nothing to do here. And then I'm starting traversal C. It doesn't have to be the next traversal. It can be some traversal down the way. It doesn't really matter. It just happens to be close here. So I'm starting traversal C, and again, after 4 nodes, I'm in node A. After 4 nodes, I'm in node 11. And that's important because now I'm understanding this happens in the runtime, and I'm saying, hey, these two traversals, every 4 node, they happen to be in the same node. So they seem to be very similar. So, you know, in these traversals, we attach some kind of dynamic context into them. And so the next time that we have to fire up traversals from the same context, or from this context that these traversals have been said to be similar, we just vectorize them. And so in this way, even if the behavior of traversals and how similar they are changes at runtime, you still can't predict that. Okay, and this is basically what gave huge speed ups in the work of this group of Dr. Kulkarni's group at Purdue. And I definitely recommend that you watch this talk. It's really great, and it goes in a lot more depth in what I just said. Okay, yeah, I didn't mean to start that. Okay, so final thing is dynamic vectorization. So dynamic vectorization to me is very interesting because it is an open problem. Okay, so it is something that has not really been solved for compilers. Compilers can't do it automatically, and there are other questions to answer, like how applicable is it? Like, for example, does it really make sense to spend some effort to realize it in compilers? Okay, let's see what is dynamic vectorization. Again, let's start with a code example to try to motivate that. So what we're going to have here is we're going to have some code. It's a lot of code, but trust me, it's really simple code. So we have this integer x here, and this integer is hopefully positive and even. And what we do with this number is we're just keep subtracting 2 from that until at some point it gives up and becomes 0. And at this point, we stop the loop. And as we're doing that, we're just tracking how many iterations we do. Now, you may have noticed that this is a really, really bad way to do division by 2, and you would be correct. But I just wanted to create an example that would be so trivially simple that we wouldn't have to think about, oh, what was this algorithm actually doing? Hopefully, everybody has understood what really this algorithm is doing. Now, before I move forward, I just want to mention that you know, when you're doing any kind of performance improvement and as you probably have guessed, we're going to do some kind of vectorization in this code. You want to compare it with the original. And this is the original. Now, the problem is that if you pass this through a compiler that respects itself, it's going to completely wipe out the loop. Okay, it's going to say, no, this is a division by 2. There are no side effects. So you're really not going to be able to compare with the original. So what we want to do here is to somehow disable the optimizer. Now, the problem is, of course, you don't want to disable the optimizations because then you're going to have stack of loads and stores everywhere, and it's going to be horrible. It's not going to be representative either. So what we want to do is we want to disable the optimizer very locally. We want to put something that's usually called a clobber. And so the act of the clobber here is to say to the compiler, hey, compiler, there's a side effect. This loop has a side effect. That's going to be what we're going to try to do with the clobber. To say to the compiler, there's an instruction, function call, whatever, that has a side effect. So please don't wipe out the loop. Don't be too smart. Now, the thing is, you could do that by actually just putting a side effect there, like a store in an array or whatever. Now, but we don't want to do that because that would actually decrease the performance because you would actually have a store in the pipeline and you don't want that. So basically what we want is to trick the compiler to try to make him think that, it has a side effect, but actually it doesn't have a side effect. And so it's really simple to implement the clobber. It's a function that basically is some inline volatile asm, and I know this looks completely terrifying. Which just basically says I'm touching some part, completely unknown part of memory. So the compiler just can't be smart here. And this is a way to where you basically in this loop, you get what you want. You really get the loop, you get how you would write that in assembly with the loop without being too smart or too slow. Okay, back to the question here. we have this thing where we just take a number, completely subtracting two, continuously subtracting 2 from that. And well, what we want to do, or what we're doing, is we have a bunch of numbers that we're going to do that for, because it's very useful. So, you know, we have this in array, and we're just taking numbers from that, and we're just storing the finish times in this outer. Cool. Now, what we're going to do is we're going to vectorize them. Okay. So the thing is, you can vectorize this outer loop, or you can vectorize the inner loop, which here is hidden inside the function. Now, we're going to vectorize the outer loop. It doesn't really have to do anything with what we said previously. It's just that here it makes a lot of sense to do that, because it's like, okay, now instead of, it's very easy to see what is happening. Instead of having one number and completely reducing it, now you have 4 of them. So visually it looks something like that. You basically, instead of starting with a scalar x, you start with a vector x. So you have 4 numbers, and you have 4 finish times, 1 for each lane. And what you're doing is, you know, you're subtracting 2 from every lane on the left, and you're adding 1 on every lane on the right. So you're subtracting 2, and again, we added 1 to every lane here, but there's a problem. And the problem really is that here this lane became 0. And that's a problem that we didn't really have in the scalar version. So the reason that we didn't have that in the scalar version, because in the scalar version we had a scalar, if it became 0, we just stop the loop and we just return. But now we can't return, because we have to continue doing that for the other lanes. So what is happening here is we have to basically freeze that, or at least this is how I call that, is we have to freeze this finish time here. It's pretty important that this finish time does not get incremented in the later iterations, because it has to stay 1, because this lane finished after 1 iteration. Okay, so the way you do that, I think you probably have guessed, is you have to sort of do predication and disable this addition for this lane. It doesn't really matter that much here. How do you do it? But you just freeze the lane. So, you know, here we did another iteration. We incremented every lane here, but we have frozen that. And again, something else becomes 0. We have to freeze this lane too. And again, something else becomes 0. We have to freeze this lane too. And now we're in a bad situation, because now there's only 1 lane that is really active. And you might say, well, at least it's as good as a scalar. But in fact, it's actually worse, because all this freezing doesn't really come for free. It's not the same as a scalar version. So we're actually slower than that, which means that this method, even if we could, you know, even if we could do this vectorization, it's really dependent on the data. I can't adapt to the data. So what we want is some kind of a solution here. And I just want to show actually how you could implement this code. I think it deserves a mention, because it's relatively simple. So here I have an artificial type, this int4, which is a vector type, let's say, so that, you know, we don't have all these horrible things, namings of the intrinsics. So what we do, you know, again, we start a finish time, we start all the lanes at 0. And then again, we assume that there's this operator is overloaded. So, you know, it's not really a scalar subtraction, it's a vector subtraction, subtracting 2 from every lane. Now for the rest of the thing, what we want to do? Well, let's see. We want to continue, keep going as long as there's at least 1 lane that is active still, right? So how do we check that? So what we're saying is, we're saying, well, do this mask again by using intrinsics under the hood, and check which lanes are bigger than 0, you know, element-wise. And the way this works is, this mask is going to get 0 for those lanes that this condition is false, and it's going to get all 1s. So every bit 1 for this element, for this lane, for those cases that this is true. Now this all 1 is going to become important a little bit. So what we have here is we have a mask that basically, if this is false for every lane, we just know that we need to stop, because it has at least 1 of them has to be bigger than 0. The final thing is, how do we treat finish time? So here's the thing: to increment finish time, to do this sort of freezing that we just said, you could do it with predication, but actually you could be a little bit smarter and get advantage of the mask. So ideally, what you would like to do is you would like to add to the finish time vector, you would like to add a vector that has 1 in all the lanes that are still active, but it has 0 in all the lanes that are not active. Now, what we have is something similar. We have a mask that has 0 in all the lanes that are not active. That's good. But it has all ones in the lanes that are active. So it doesn't have 1, the value 1, it has all ones. But all ones is really -1 in twist complement. And that's great because instead of adding the mask, you can just subtract it and you have this freezing behavior. Okay. Now, back to our problem, which is really that depending on the data, you can have a lot of inactive lanes here. How we can solve that? So here's a way that you could approach this problem. And I guess a lot of people, such problems exist for a lot of years in vectorization. So a lot of people probably are going to have more ideas on how to solve that. But here's one idea. So you could say, okay, I have this this data here. This is my in array, my input numbers, and this is where I'm going to store my finish times. So what I'm doing is I'm taking 4 numbers, and then I'm doing what I was doing before. But now, when a lane becomes 0, instead of saying, oh, I'm going to freeze that, and I'm just going to keep going, what I'm going to do is I'm going to immediately store its finish time. Now, there's a question here. Where do I store the finish time? How do I know where this is supposed to be? Let's pretend for a little bit, because this is really not the point here. Let's pretend that we do know where to store them. Okay, and we're just storing it. Then we're bringing a new number in this lane that just finished. Okay, second question that is kind of important, but sort of besides the point here, is where do you bring a new number from? So here, let's assume that we just know where to bring a new number from. Okay, and so we're bringing a new number and just continuing doing that. So now we don't have inactive lanes. Okay, so to replay that, here's another lane that has become 0. Immediately storing its finish time, bringing a new number in, and we're just continuing. Now, another question here is, which again is sort of has become a theme here, as we're going to pretend that we just know how to do it, is when does this finish? Because previously it was pretty easy to see when did it finish, right? It's just when all lanes become 0, you just stop the loop. Okay, sure. But here you're continuously having new lanes going in. So how do you know? Again, an interesting question. We can discuss this into the Q&A. But for me, the most important thing that I absolutely have to mention, because I think this is a more important thing here, is we have an operation. It's really a subtraction by 2 that is totally trivial. It's a very simple operation. And you might think that by doing all this trickery, like, okay, finding out that this became 0, storing the result, but storing only one part of the lane, bringing one part of the lane in, it's going to require some slow instructions. And indeed, the way I implemented that is by using predicated scatters and gathers. You could do it with multiple mask loads and stores, but the point is the same, which is that it's very sensible to assume that all the scatters and gathers, or anyway, the way that we have implemented that, it's a lot of trickery. It's going to completely dominate the running time. This can't be faster than the statically vectorized version. And actually, the reason that I present this today is because it was a great surprise to me that this was actually faster. I think it was a significant speed up. It was 1.25 times faster than the statically vectorized version, not from the original serial version, but from the static vectorized version. And that was for random data. So again, I would love to have benchmarks and even a paper on that, but it's just very preliminary work. It was just something that we found interesting. I heard about that, and I thought this is interesting to show people that this might have some future for compilers. But again, still there are questions to be answered, like, when is this applicable? Does it really make sense? Is it really worth it to try to do something like that in compilers, and all that? So I'm going to finish somewhere right here. So thank you very much. And I want to give some acknowledgements to some people that gave feedback to this talk. So thanks to the group from Princeton and Purdue, and thanks to Simon Moll.
Great. Thank you for your talk. It was very informative.
Thank you.
We already have one question in the chat that I will ask David to potentially read it, like ask himself. David, do you want to ask a question? You should be able to unmute now. Okay. In that case, I'm going to ask, so regarding the tree traversal optimization, is it somehow related to profile-based compile time optimizations?
Yeah, now you should be able to hear me. All right. Not really. I mean, I guess you're talking about PGO, which is usually, well, I mean, it could be. The papers that this presentation is based on are not really profile driven. It could be, you could say, okay, I'm running some indicative cases, and then I'm gathering data and I'm saying, hey, I'm deciding at compile time. So let me actually go back to this. So, again, the problem is, how do you make vectorizations that, how do you find traversals that visit the same nodes? So it could be profile driven. You could just do profiles and say, okay, these traversals seem to be like attach some dynamic context and all that. And say these traversals seem to be to follow similar paths. I guess you can't really cover the case where the behavior changes in the program. But here, this kind of technique was really presented not to be profile driven, was presented as something that you don't really know the semantics of your program. I mean, you could also drive such kind of decisions if you know more things about semantics in this kind of similar reasoning with a profile guided thing. But yeah, this was presented as we have some kind of traversals. We really don't know much about that, and we're trying to find out in the runtime.
Okay. A question of mine. So the dynamic vectorization in the end you presented reminded me a lot of these GPU techniques where they
compress and expand.
Yes, where they swap in GPU threads and so on and so forth. So you think that there is some overlap and some way to reuse that or make that kind of part of the middle end instead of the GPU runtime?
Sure. I mean, I think that basically it's sort of the same problem that you have starvation, and you're sort of trying to kind of somehow alleviate that. I think that we should. The first thing that has to happen here, and that was actually a very clever comment from Dr. August, which was that, okay, how applicable is this? I just don't want to take the credit for this comment because it was very great. It's like, okay, sure, the compilers don't do that, but would it be useful if they did that? Like, how much useful is that? And personally, I don't know. The way I learned about this technique is from a paper that was not really in a compilers conference ever. And it just presented the case, like how you can do it, but not at all automatically generated or something like that. As far as I know, there is not really a study on how applicable is this to general purpose code. And I think that would be the first step towards this direction if people find it interesting.
I guess we first need to have outer loop vectorization, or at least vectorization of things where we have early exits in order to really do the measurements and figure out how many inactive lanes we have, right?
Sure. Yeah. I mean, I think that you know, we're working together with Zimmermol. I just didn't want to just promote too much the region vectorizer, but it just happens that the region vectorizer is a really powerful vectorizer. It can vectorize. I mean, so for example, in the paper, in one of the really important papers that the region vectorizer is based on, they presented 3 traversal vectorization. So it can vectorize really arbitrary stuff. And the reason I'm mentioning that is, if we want to start taking vectorization from some very applicable cases and doing something more generic, we need vectorizers that, you know, they can go bananas. They can just vectorize really strange code. And this is the reason that I think it's interesting. Well, yeah. Sorry. It's interesting to see the region vectorizer more as a community. But it's not really, the point is not really only, you know, generally we need powerful vectorizer. It just happens that this is what I know. Yeah, sorry, please go on.
No. You, like, for what it's worth, I agree. And I would love to see us starting to integrate the region vectorizer as a opt-in into the LLVM community version. I would love that to happen. Okay, great. Thanks again for your talk. And we're at the last talk in this session now. Alexis, wait, let me try.
Okay, thank you very much, everybody. Bye-bye.
Okay, perfect.
All right, so can you hear me?
Yes, we can.
That's great. All right. So I hope this is working.
Yes, and the floor is all yours.
Great. So hi all, I'm Alexis. I'm going to talk about the Instrew project or how to do fast LLVM-based dynamic binary instrumentation and translation. So first of all, what's dynamic binary translation and why are we doing this? So say we have one program compiled for our legacy x86 machine, and now we have our brand new ARM machine and we want to run this old program because we don't have the sources available. We somehow need some way to run this program. So interpretation is slow, so what we actually need is we need some way to translate code from our host architecture or from our guest architecture to our new host architecture. So for example, from x86 to ARM. So use cases are compatibility mostly, but also for architecture research, this is very important. So you can try out new ISAR extensions and experiment with that. So the most popular example is QEMU, which supports many guests and many hosts, but also, for example, with Apple's new Rosetta 2 on ARMX, and also Windows has a similar translator. So this is actually becoming more popular again. So far for dynamic binary translation, so the key thing is we have one architecture, which is we have the program in, and we have another architecture we want to run the program on, and we just wanted to behave. We would just want that the program behaves the same. Now for dynamic binary instrumentation, we want to modify the program behavior. So for example, we want to add additional code or checks. So most popular example is probably Valgrind, where it's adds some memory region checks and addressability checks and inserts this dynamically in the program so you don't have to recompile. But there are also other use cases, for example, profiling tools where we instrument, for example, stores or loads and check what data is loaded or stored and perhaps implement a cache simulator on that. So these are other use cases of instrumentation. And also for architecture research, for example, instrumentation is used, for example, of ARM. I know that we're using it to develop new ISAR extensions. So examples for DBI are Valgrind, PIN, and there are a few other frameworks. So, well, we have two problems, we have solutions. So what's actually the problem? The problem is that many frameworks or systems for dynamic binary translation or dynamic binary instrumentation focus on the translation performance. So for example, QEMU, Vagrant, PIN focus on getting code running fast. No, well, not running fast, but getting code running with lower time difference. So yeah, and therefore neglect that the actual code they produce, for example, for the other architecture or for the instrumented code, is slow. And this is a problem especially for longer running applications, because if you add some heavy instrumentation in your program, your slowdown can easily go into the regions of 10 or even 100 times. So you want that the code you generate is fast. And if the translation then is not like 10 milliseconds, but 10 seconds, if your overall program run is like several minutes, you definitely want to take that cost. So what we're going to do instead is we are using LLVM for runtime performance. So we try to use, or we're going to use LLVM to generate new machine code for the DBT use case, for the other architecture, or for the DBI use case for our new instrumented code. And we implemented this in Instrew, which is a fast LLVM-based framework for DBT and DBI. All right, so how we are going to do this? Well, step one is, as first step, we have to do the heavy lifting. So we need to lift machine code from, well, we need to lift the machine code to LLVM-IR, so we have the semantics in place. The second step is that we need to align like the DBT, DBI environment for the LLVM code generator. So LLVM is designed for compilation and, well, running in like a C-based environment, essentially, and not for working on binary code. So this needs some minor adjustments. And step three, well, profit and enjoy the new performance gains. So before we're going into these three steps, let's first revisit how DBI and DBT works. So let's start with a look at the process level dynamic binary translator. So essentially, we can split it into two components. The first one is the execution unit, and the second one is the translation unit. So we start with the execution unit, and at program startup, we have our guest program, which is what we want to execute, for example, our x86 code, and we want to run it on our ARM machine. So what we do at first is we load the new x86 code into our address space, so we have it accessible, and initialize our emulated CPU state. And when we enter the main loop, and within the main loop, the execution manager looks at the program counter, checks, okay, we are at this guest address, and then triggers the translation process. So the translator then decodes this code, lifts it to some probably architecture independent code representation, which is then compiled for new architecture, in, for example, ARM. And this is then placed into the code cache. And then when this code fragment is executed, and once it's finished executing, it updates the virtual CPU state. And then the execution manager looks again at the new program counter and sees, well, do I have this address already translated in the code cache? Then it uses that again. Otherwise, it triggers a new translation process. And this process repeats until the program terminates. So if we add dynamic binary instrumentation to this picture, it actually looks very similar. So the only two differences are that after decoding and lifting, it may be an architecture dependent IR. So for example, if we run x86 and x86, we may not want to throw away our previous x86 instruction, so we can get faster from x86 to x86. And after lifting, the code is actually modified, which is instrumentation. But the rest is actually very similar, and especially the execution unit is actually very similar. And translation now essentially becomes a special case of instrumentation where just the instrumenter doesn't modify anything. So what we are going to do is we are going to unify these two things into our generalized transformation unit. So we decode lift, then as architecture independent code representation, we use LLVM. Then instrument, perhaps with just doing nothing, and then we generate new code. So that's how it integrates. So let's start at the top with decoding and lifting machine code to LLVM. So this is actually a widely researched field, and there are many lifters available out there with varying quality. So the probably best and most tested and lifter with the best coverage of instructions is MC-SIMA, which is designed for binary analysis. So they do a lot of analysis steps, and we have an extra intermediate representation before we go to LLVM, and we try to recover functions and global variables and calling semantics and calling conventions from machine code. But the downside is this analysis makes it very slow, and therefore it's not really the best candidate if we care about performance. So the other working and lifter with good support is implemented in HQEMU. So what they do is they actually go first to TCG, which is the architecture independent code representation from QEMU. So we use QEMU to lift it to its TCG intermediate representation, and from there go to LLVM. The problem is that TCG only supports basic blocks, and having an LLVM function for a single basic block and doing this for like tons of basic blocks you may have in your program is slow. So what we do instead, we work around this issue by using traces of TCG blocks and lift traces to LLVM. But ultimately they are still bound by TCG, and that's a limiting factor which we try to avoid. A more recent approach is MC2LL, which is also more targeted binary analysis and static lifting. The problem with MC2LL is simply that it has very low instruction coverage. So for example, it doesn't cover any SSE instructions or any meaningful subset of SSE instructions. I think it covers 2 out of more than 100. So this is definitely not usable in its current state. So this means we have like a ton of lifter, but these are either not fast or they are not have a bad coverage. So we need, unfortunately, but we had to roll our own lifter, which we call Relume, and this is our performance-oriented lifting library, in which we try to avoid all the mentioned problems. So what's the point? The point is we want to go to target independent and idiomatic LLVM-IR, which means we want to use LLVM constructs wherever possible. So for example, if we have a vector instruction in our machine code, then we want to use LLVM vectors. If we have like comparison instructions like above equal, then we want to lift it to an unsigned greater equal comparison LLVM-IR and not have this bit twiddling hacks. And we essentially in mind that we want to recompile it to another target. For some things, it's impossible. So for example, for system calls or for x86 CPU ID, these are lifted to helper functions. The other key point is that we care about the performance. So we try to avoid heavy transformations like mem2rex. And for example, for the mem2rex case, we just generate phi nodes directly and avoid such transformations. So essentially running 1 times ins combine and DCE and simplify CFG is usually sufficient to get very fast code out of it. So how does it work? So in the first step, we decode instructions and recover the control flow from the machine code and split them into basic blocks. Then we lift the individual instructions and basic blocks to LLVM-IR, and in the third step, we can then fix up the branches between the basic blocks and fill the phi nodes with proper values. So currently supported architectures are x86-64. The base instruction set has a very good coverage and only misses like 8 or so out of 200 or so instructions. RISC-V is also supported, whereas an ARM port work in progress. ARM is also a very big instruction set nowadays. So this will probably takes few months still, so that it gets a meaningful coverage. All right, so how does the lifted code look like? So in this case, we are going to lift a single instruction, which is a sub RSP 176, which is in this case completely arbitrary, but just for the sake of showing an example. And what we see here is that this x86 subtract instructions is lifted to an LLVM subtract instruction, and we have no loads or stores associated with it, and there is some compute flags involved because subtraction x86 sets some nasty flags, but these are usually collected by the DCE again. Well, so what we also can see is that we have a phi node in here, which somehow needs to get filled. And we see that, of course, we have all this code inside the function, but the function is not a meaningful concept in raw machine code. So how do we map machine code to LLVM functions? Well, so whenever we lift some machine code, we put it into a single LLVM function. And this function takes a single parameter, which is a pointer to the CPU state, which has few more attributes, which are omitted here for brevity. And this contains everything what is essentially needed for the CPU. So it has an instruction pointer, register, status flags, and all the things you need. And in the entry basic block, first of all, well, we need to construct pointers into this big structure. And then we load all the registers into SSA variables, and which are then propagated throughout our lifted code. And yeah, with like many phi nodes for more complex codes. And these are only written back in the epilogue, where the so right before the function returns, these values are written back into memory, and also the new program counter is written back. So as you can see, we start lifting from a single instruction, and when we discover all the control flow, we can reach from there with direct jumps, map this control flow to LLVM, and once this function executes, it updates the CPU as if the real machine code would have been executed. All right. So the good part is this is functional and this is fast, and I'll go into more details when I get to the performance. Let's talk about the downsides first before talking about the upsides. So there are some limitations imposed by LLVM. So the first one is, well, we keep our CPU state in memory, and if we switch between such code fragments, we have to write all our state in memory, and this is bad. So for x86, there is a broken HSVM calling convention, so it's not broken in the sense that it doesn't work. It's just broken in the sense that you can't meaningfully call our function because it breaks a stack alignment. But for other architectures, there are no such calling conventions. So this motivates the need for general or registers calling convention, which is just more flexible, and which allows to like directly access and add more register constraints through the function definition without using inline assembly tricks. There is another limitation which I didn't found time to investigate yet. So when we use LLVM instead of LLVM 9, the generated code is on average around 40% slower. So this is still something I need to investigate. The ugly parts are, well, there are some hard problems with dynamic binary translation. So floating point semantics are definitely one part, because the rounding mode depends on the runtime register, which is currently impossible to model in LLVM IR. Currently, we ignore rounding except for floating point integer conversions, in which case we have to resort to software emulation if the host doesn't support required instructions. The other two things are locked store conditional atomics, which we typically find with RISC architectures like ARM or RISC-V. So this can't be represented in LLVM IR. And well, ideas are to use hardware transactional memory, but I will not go into details here. And the other issue is memory consistency. So if we want to run multi-threaded x86-64 on any other RISC architecture, we are faced with the problem that x86 has much more strict memory semantics than everything else. So an open problem is whether LLVM analysis can help here to reduce the number of fences you need to insert, or if you really need to get hardware support that you want to run this fast. And hardware support is also the way, for example, this is implemented on a new ARM Max. Okay, so that was about the lifting part. The instrumentation part is actually a bit more easy. So we implemented this in the client-server approach, which is more flexible. So we have a client which knows nothing about LLVM, and we have a server which knows nothing about the code cache and things like that, and really concentrates on translation. So this is more flexible. For example, the server can also run on a different machine, or can be run permanent, or we can add a new layer in between, so that we have a caching layer which intercepts requests and uses them from previous runs to avoid heavy translation. And MCJIT generates ELF files, so the client is essentially a very simple ELF linker. Instrumentation works on the server side. So this is a shared library on the server side, which can do two things. The first thing it can do is it can initially load library functions into the client. So this is usually realized by loading some LLVM bitcode and compiling it on start for the target architecture and send it to the client as ELF object. And whenever code is lifted, the tool is called to modify or instrument the function. And once it's finished, the code is then optimized and compiled and sent back to the client. So one problem is memory management, which is currently rather simple. So currently there are 48 bytes storage accessible in the CPU state for the instrumentation tool. And if the tool needs more memory, for example, because it wants to shadow main memory, it needs to currently to do the memory management itself. And this is kind of tedious because the tool runs on the server side, which is a different process, so it can't directly access client memory. So it needs to have its own client functions for memory management. This is currently a bit ugly, but it's not a real limitation. Okay, so let's talk about the functional and fast part. So we did run it on spec CPU 2017 benchmarks. So there is only one benchmark which currently doesn't work, which is the Perl benchmark, for two reasons. First of all, clone is not supported, the system call, which is used to spawn new processes. And on x86, it uses FPU instructions, which are currently not lifted. Yeah. But besides that, spec works. And for source architectures, we currently support x86 and RISC-V. And for host architectures, we are currently supporting x86 and ARM. To show good numbers, these are the numbers still obtained with LLVM9 until I found time to figure out what's wrong with LLVM11 and compare it to Valgrind, the number RIO, QEMU, and HQEMU, which are mostly the state-of-the-art tools. And the baseline is, so the one in this normalized graph is the native execution on the host. So if we run it on, translate something to x86, we compile the benchmark natively for x86 with all optimizations enabled and see how much distance is there from our generated code to the optimal code. So what we see here is that Valgrind and QEMU are on average on the integer benchmarks rather slow, with a slowdown of ranging from 3x to 5.5x. HQEMU, so this is a QEMU variant which uses LLVM for post-processing traces, is slightly faster than QEMU, but our approach, which avoids TCG as intermediate code step and just goes directly from machine code to LLVM is, yeah, in all cases better than HQEMU. So for example, for x86 to x86, the overhead is exactly half from HQEMU. For the instrumentation tools, I also added the Namu-Ryo in this plot, which is kind of an unfair comparison because the Namu-Ryo does literally 0 optimizations and reuses the original code as far as possible, which is kind of cheating if you compare with a tool which goes to a very high-level abstract code representation. But it serves as a baseline. How far are we away from like where we actually want to be? So these are the detailed results for x86 to x86. I don't have too much time right now to go into the details, so I'll just point out 2 things. So the first thing I want to point out is the best case, in which Instrew has an overhead of just 7% compared to the native execution, which is better than HQEMU. And the worst case is that Instrew has a slowdown of factor 4.2x. So usually it's below factor of 2, but for GCC it's even worse than HQEMU. The reason is that in this benchmark, 55% of the time is actually spent in LLVM for generating code. And well, GCC is a notable exception, where it just executes a lot of code. Yeah. So this is one point where writing time matters, and also for the HHVM calling convention, which I mentioned previously as optimization, where much more register constraints are added to the compiled code. The code generation time also increases between 12% and 78%. So I haven't digged into why this is the case, but I just assume that the register allocator gets slower if it has more pressure. And if we look where the writing time is spent, we see that the lifting and the optimization part is actually not the problem, but the problem is code generation. So selection DAG is slow. And global ISIL is work in progress, and will be interesting to see whether global ISIL will be able to achieve significant improvements on this fraud. Okay, so to conclude, Instrew is a fast dynamic binary instrumenter and translator based on LLVM, where whole functions are lifted to LLVM-IR and then instrumented and then translated to another architecture possibly, and it exhibits a client-server approach enabling further optimizations, and compared to HQEMU, which is probably the state of the art for LLVM-based DBT, it has 50% less overhead on the x86 to x86 case. And of course, Instrew is open source. You may expect some rough edges, but if you really want it, you can try and send me bugs. Thank you for listening, and I'm happy to answer your questions.
Great, thank you. We're pretty much tight on the time, but we'll have a few questions. At least I have a few questions, and if people want to type their questions in the chat, I'm also happy to read them out loud. Great talk. There was like one thing that surprised me is when you said that you avoid heavy optimization on the LLVM-IR level, and so in the end, it looked like the optimization are not that much of your overall time, right? It's like 22% right now, which is still, I mean, if the optimization adds a little bit there, but gives you better performance, it might still be worth it, right?
Absolutely. The point is that, so I tried with adding like, for example, loop optimization passes or revectorization. The point was that it didn't improve the overall performance much. So for example, on some parts were better, other parts were not, and overall it didn't make a difference on the didn't make a very significant difference on the actual code with the null instrumentation. Of course, if you add some more instrumentation to your code, for example, whatever profiling or memory checks or whatever you want to add there, then of course you do want to profit from LLVM's rich optimization framework, and which also was the main motivation for using LLVM, because when you have these optimizations already available and don't have to implement them yourself.
Right. And the one thing on your slide said that mem2rec is heavy.
Yeah, it's not heavy itself, which was a very short. So it is heavy in the sense that if you have, so if you generate code in a memory fashion way, you have like load register, subtract, store register, and you have this like several hundreds, thousand times within each function. Yes. And if you apply mem2rec, it adds a considerable amount of time, because it just walks through every single part of the code before even DCE can meaningfully throw away things. So in this case, it's just more efficient to do a bit more work and bookkeeping yourself and avoid mem2rec.
That is interesting, because like in my experience, if you you said you generate finals yourself, but in my experience, if you stick with allocas too long, a lot of other optimizations and analyses passes as well will work way worse. So they kind of require you to promote all the allocas as aggressively as possible early on. Otherwise, they will be very conservative. Have you?
Sure. And so that's the reason why I don't emit allocase at all at the moment.
You don't emit alloca instructions. Okay, yeah. Well, we can take this offline. Okay, and then I had a second question. Oh, you said the current limitation about the floating point. There was a limitation about floating points, right? That you mentioned.
I actually have a dedicated slide on that. This one. Yeah.
Okay, why? Have you seen the floating point intrinsics, the LLVM experimental constraint floating point division, floating point rem, and so on? So those, sorry, yeah, go for it.
Yeah, go ahead.
Yeah, those intrinsics are supposedly take the rounding mode exception behavior as part of their invocation. So you can encode rounding mode and floating point exception behavior as part of the floating point operation, and they have been merged in 2016.
Yeah, I'm aware of that. I'm currently trying to remember what the problem was. I'm not quite sure. I think the problem was that it only affects the semantics when optimizing, but it doesn't affect the semantics on the code generation side. So if I have an ARM instruction which says I'm rounding like towards infinity, and if I want to compile it on x86, you need to adjust the rounding mode register if you want to do that, because x86 has no instructions that lets you do this directly. And I think CodeGen just ignored that and just generated a normal truncating conversion. And this ended up with mixed semantics. So when it's optimized away, it would be correct, but if machine code is generated, then it would be wrong. So that was the problem, if I remember correctly, but I'm not 100% sure on that.
You know, that might be, and it could be that the expected usage is to use those intrinsics together with the set rounding mode, but certainly something to look at, especially if it's problematic for you. Maybe you can even extend the upstream support.
Yeah, I'm definitely planning to look into that.
Right, perfect. And
thanks.
We have one more question from the audience. William asked, for the memory consistency challenge, as you mentioned, apart from fences everywhere and hardware support, if there's any hope for tools to add fences at the right places?
Yeah, that's the hard part, isn't it? So the hard part is that you actually need to know about the program and what all the other threads are doing so that you can omit fences. So I'm not aware of currently techniques to omit these fences. One slight hope I haven't given up yet, probably due to lack of research, is that if we have all the program semantics in a well-defined and a good, well-analyzable representation like LLVM, that we can do more analysis on that and perhaps find better ways. But I'm essentially not really sure about that. So there is probably some hope, but I won't set hopes very high.
Okay. There is a no-sync function attribute in LLVM IR nowadays that the attributor can derive. And so you can at least, for certain situations, figure out that there is no cross-thread synchronization possible, which might help in towards that direction.
Okay, thanks for the hint. I didn't knew that. I'll definitely look into that. Yeah, thanks.
Yeah. Okay, so I think we are already running into our break time. We are.
Yeah.
So we're reconvening in 10 minutes.
Just a short update that after the break, Dennis will be presenting. I updated the schedule on the LLVM dev meeting website, but like updating on WOVA was a lot of work. So, so there are only 2 presentations left. I'll be the last one.
Okay, perfect. Thanks, Alexis, again. Great presentation. And we'll reconvene in 10 minutes.
Hi everyone, it's Dennis. Can you hear me?
Yes. Let's wait for another 2 or so minutes before we start.
Sure.
We can also see the screen fine.
Oh, thanks.
By the way, your tweet brought a lot of attention to people, Dennis.
Yeah, I actually have it in my slides.
Oh, you did? Okay, that's a good strategy, actually.
Yeah.
Nice. Johannes, are you on Twitter?
No.
Okay, good for you. It's like, it's a time killer, basically.
I read the LLVM dev list, so.
Okay, that's.
Yeah, I asked the same question on their list as well.
Yeah.
Just, you know, was trying to collect some wisdom.
Yeah. Should we start or it's like 1:31?
Yeah, wait for like.
Okay, we can wait another couple of minutes.
Yeah, we said like at 22. I said 10 minutes, so at least wait till.
Okay, give 2 more minutes.
Okay, let's start.
Sure. Okay, so hello everyone. My name is Dennis. I'm a compiler engineer at Intel, and today I would like to talk about about future compiler improvements and in particular what will drive further further performance improvements in the code that we generate. Okay. Let me see. Okay. And so we live in an increasingly data-centric world, right, where we generate enormous amount of data every day. And so, and of course, this fuels the need for, faster processing of that data, right? But unfortunately, the modern hardware does not enjoy the same speed ups as it used to, during the past decades, right? So on this chart, you can clearly see that, performance of a single-threaded performance is reaching a plateau, right? And single-thread performance is still important nowadays, right? And essentially, so what that means, it means actually that the easy ride for software vendors, so for software vendors is over, right? So they cannot rely on hardware anymore, and they need to start, and spending some efforts on making their code run faster, right? And there is the recent paper called "There is Plenty of Room at the Top," which outlines the 3 key areas where the performance improvements will come from. And so one of the area is hardware streamlining, okay? And we already see this, we have a whole bunch of different accelerators, right? That are there are still, many areas where the research is quite active. So for example, machine learning, and also AI can, discover some new interesting approaches to the existing problems. And then the third area is software performance engineering and tuning. And this is the area where a lot of improvements will come from, application developers improving and tuning their code, but also this is the area where we as compiler engineers can make an impact. And well, performance engineering is hard, right? And unfortunately, not every application developer is a performance ninja, right? So, and I believe they will hugely rely on compilers, on us, right, in this battle. And so, we are on the spot, right? People still expect us to deliver, better quality compilers. Oh yeah, and by the way, I actually wrote a book specifically for application developers, which is called Performance Analysis and Tuning on Modern CPUs, and which tries to teach, application developers how to find bottlenecks in their code and fix them. Okay, and so the book is divided into 2 parts. So first is about performance analysis, and it goes from the grounds, from the basics of microarchitecture, and it introduces the popular performance analysis approaches like flame graphs, like roof lines, and some hardware specifics. But finding the bottleneck is only half of the problem, right? The second is actually you also need to fix it, right? And the second part of the book is all about tuning, how to work with compiler, to fix, and clean up all its shortcomings, right? So AKA, beat the compiler. So you see, oh yeah, by the way, so the book is actually the PDF version of the book is available for free. You can download it using this link. And so this is my message for application developers, right? And I began thinking like, well, okay, so I have this message for application developers, which is about that they should become better at optimizing their code. But what would be my message for compiler developers, right? So especially being a compiler person myself. So I talked to a number of compiler experts and asked them basically this question, okay? So how we can further improve the performance of the code that we generate. And what I will present next is actually, is the summary of the wisdom that I was able to extract, okay? And yes, sure, now we also live in the increasingly heterogeneous world, right? But for the purpose of this talk, we will concentrate just on a, let's say, classical CPU compiler. And so the first area is, synthesis and super optimizers. And the paper that I show on the right, which is by, Nuno Lopez and John Reger, talks a lot about this concept. So this is the search-based technique where you start from some program. It can be even an empty program. And then you perform some transformation to the code, okay? So it can be even a random transformation. And then you evaluate the cost, okay, after that. So the cost function here could be correctness, but also performance, okay? And I should point out that it can take a million steps until you get the first, correct program. But in the end, you will not only, get the correct program, but also the fastest one, okay? And I believe there is still a long way until we will see, some production level compiler that will be, fully be, built on top of this technique. However, super optimizers prove themselves useful for small programs. Okay, and so for example, super optimizers like Stoke and Soper were able to find missing peephole optimizations, for example, in LLVM inst combine. And so, as to me, I believe that right now it's more about filling the gaps in existing peephole optimizations rather than having rather than fueling the whole compiler. Yeah. And I think the reason for that is that there is a huge challenge to overcome actually for super optimizers. This is the compilation time, right? So you see, we cannot afford, running the super optimizer, which will run 10 times longer, but will generate only like 5% better code, right? The second area where I see the future efforts is breaking down passes and decoupling legality analysis and cost model from the transformation itself. Okay, and we already actually see this coming. The LLVM inliner pass has this so-called replay feature, right, which allows you to dump all the inlining decisions in a text file and then replay it from this text file. Okay. And this enables quite interesting opportunities for us, right? So we can replace the cost models with the machine learning model, right? So this machine learning model can easily, generate this text file for us, okay? So you see, the cost models and heuristics are all about, no one really, well, okay, I should say few people know how they work. They are really complex, and they are designed for what usually works best, in benchmarks. However, I believe that machine learning models can do better than that. And then the second area is that machine learning can steer the whole optimization process. Okay, so it can decide what transformations to make, and can also decide the order in which to make them. I think there is one interesting advantage to using those kind of models is that we can build the compilers for new hardware generation much faster. Okay, well, because for every new generation, for every new hardware, we don't need to tweak the heuristics and write new code. Instead, we just need to train the model. The third area is auto-tuning and re-optimizations. So as a background, right? So a lot of decisions, a lot of optimization and transformations can be done better if you have the profiling information at hand, right? And languages like Java, for example, already leverage that. There's a hotspot JIT which constantly re-optimizes the code as it runs based on the profiling data, right? And they also do so-called heroic optimizations, which are quite useful in some cases. And there is the early evidence that we might have the same in C++. There is a talk by Hal Finkel made a few years ago about JITing in C++, right? And the second point I try to make here is that hardware telemetry data gets more advanced, right? So it allows to observe things like cache misses and branch miss predictions much better than before. Okay, so for example, in the newer Intel CPUs and modern CPUs, you can detect the exact assembly instruction where the most amount of cache misses happen. And also, if it is a linear code, you can also estimate the prefetch window in CPU cycles. Okay, so and based on this data, you can actually you can intelligently insert the memory prefetching hints. Okay, so well, because first the exact assembly instruction for which you need the prefetching, but also you need the how much before this instruction you should insert the prefetch hint, right? So I believe that the profiling data can be richer than it is now in LLVM. And also potentially more passes can be guided by this profiling data, okay? So memory prefetching is just one example. Another example can be, we can do smarter, I would say, branch to CMOV conversion based on, the profiling data. And the next area is optimizing libraries and abstractions. So in the example of code here, there is a loop which does 1,000 times pushback, okay, which does a fair amount of unnecessary memory moves, right? Which could be, saved if you would call a reserve function ahead of time. So you see, and I think this is the example where compilers can and should, help to improve performance. So the generalized statement of the problem is, is we end up optimizing C++ if it is C, right? So we analyze pointers and calls, and unfortunately we tend to lose, high level semantics of the code and abstractions, right? And other languages seem to do better here. For example, like Swift and Rust. I believe there is no easy solution in C++ to this problem. We can either come up with a high-level intermediate representation that will capture this high-level semantics, or we can tackle it with some kind of annotations. But both options seem quite hard because LLVM is a mature infrastructure and changing it is hard. But also, besides directly improving the code, right, we can empower developers to to fix their performance issues much easier. Okay, and I think that current technology is on its way, to provide all sorts of recommendation systems. So, and for example, what I show on the picture on the left is code similarity analysis. So imagine if we can extract the semantic meaning from the source code, and we can linearize it in some way. Okay, so then we will able to compare the code by if it is similar, right? And this enables actually quite interesting use case for a recommendation system. So imagine that we, for example, collect the database of the code written by performance ninjas. Okay, so you can view it as, for example, the best version of, let's say, matrix multiplication code, for example, for AVX2 processors. Okay, so and then the next time developer will write something similar, we'll recommend the already existing, best performing version to the developer, right? And so the recommendation system will be like, hey, okay, so I think you are writing the matrix multiplication code. Do you want to reuse the code written by performance experts? Well, if yes, here is the diff, right? And I believe that compilers will play, a big role in building such kind of systems, recommendation systems. So I did a poll on Twitter, actually, and basically asking the same question, right? So what will drive future performance improvements in compilers? And I will give you just a couple of seconds, right, to familiarize yourself with numbers. So as you can see, there is no particular leader here, right? So and to me, it seems that there is a lot of uncertainty in the community. So what I found actually in discussions that still a lot of people think that and still a lot of people are skeptical about those fancy new designs and and innovative ideas. Others who believe that compilers will step away from the traditional design and will do more more, let's say, sophisticated things. They still agree that it will take a lot of time until we see something like that. So and I think the main challenges for for those innovative ideas are first is verification. So you see, for machine learning model, it's perfectly fine to be 99% accurate, right? However, for compilers, it's pretty much a game stopper, right? We cannot allow to generate incorrect code even in 1% of the cases, right? So we need some kind of formal verification methods here. The second challenge is compile time trade-offs, right? And some domains will prefer 2 times faster compilation time instead of, for example, 10 times better runtime performance of the generated code, right? And then the second challenge is pretty much simple, because changing LLVM is hard, right? Adding new instruction into LLVM, is painful. I'm not talking even about, designing and implementing the new intermediate representation. And so the takeaways, the free lunch is over for software vendors. Software tuning will become one of the major drivers for performance improvements, and obviously compilers will play a big role here. And so the key areas for future compiler improvements, first is replacing cost model and heuristics with machine learning. Second is filling the gaps with super optimizers. Third is making better use of profiling data. Fourth is doing a better job at optimizing libraries. And number 5 is helping developers to solve their performance issues. And that's it from me. Thank you very much for attention.
Great, thank you. So we're a little bit over time, but I don't think it is bad. We should have time for a question or comment or two. So David had a comment in chat. David, do you want to? Oh no, you don't have a mic, right? We said we have got rather good results when optimizing GPU codes using performance counters. See searching CUDA code auto-tuning space with hardware performance counters. Do you think that one of the possible ways for additional performance would be a programmer-assisted auto-tuning?
Let me see, programmer-assisted auto-tuning. I'm not sure I understand what this means. So program-assisted auto-tuning is some kind of hints or I don't know.
Yes, why not?
Like Pragma, I guess. Pragma is one, right? You have Pragma, so OpenMP Pragmas, for example.
For what it's worth, we added into the OpenMP 5.1 standard an assume statement, which allows the compiler to basically ask the user for more or less arbitrary information and can say, hey, I need to have this high-level information. Can you assert that for me? And then the programmer can do so in a relatively straightforward way through a pragma.
Oh, that's actually nice. That's nice. Yeah, I agree. This is actually really nice. So it can be even a warning, right, or some kind of remark.
Right. So exactly. The currently we have one user that is the OpenMP optimization pass that is OpenMP aware, that can ask the user to add some annotations that it can then use, like high-level information about the use of OpenMP.
Right. I think that's great. That's great.
And for what it's worth, the implementation in Clang also allows you to use this without having to go through OpenMP pragmas, just if people don't like OpenMP too much. You had a lot of good points on your slide, but one thing that I hear a lot and that researchers do a lot is this learning optimization pipelines. And the one problem with that from a practical perspective is testing. Like, how do you test or like continuously test your optimization pipelines if they are variable or if you have too many of those? Do you have a comment on that?
Right, that's actually a good question, and I believe so actually, yeah, I pointed out, right, so because this is the challenge actually. So verification is a big challenge here, but I believe we already can prove and compare code by equality, right? So for example, in those like super optimizers like Stoke and Super, they are sound, right? So that means that they can prove that that the baseline program and the program that they were able to synthesize are equal, right? So I think we should go with something like this.
Okay, that makes sense. So David clarified, basically programmers define multiple versions of a program. For example, we have defines, and then the library tries multiple versions of the code based on the available hardware being processed. It's okay. Do we have other questions? I had some, but I will probably take them offline because it's pretty late. Thanks again for your talk. Really interesting.
Thank you very much for having me. It was a pleasure.
And then Aditya, you're up last, right?
Yeah. So I can share the screen basically. All right. Is it visible?
Yes. It's not full screen yet, but visible.
Okay. How do we do full screen? Let's see. Okay, awesome.
Perfect. You're up.
All right. Yeah. So hello everyone. I'm Aditya. I work as a software engineer at Facebook, and I've been working as compiler engineer on performance of system software. So here today's presentation is about performance improvement opportunities in the open source C++ libraries. When I say open source, I'm mostly talking about libc++ and libstandard C++. So the first question is like, why even bother, right? That library is so complicated. Nobody even wants to look at it. And even if you have some courage to look at the code, it's written in a way that's like, that would just, is not very readable. You have like too many underscores, leading underscores, and macros all over the place for versioning, and namespaces all over the place, and no comments. That is another problem. So why even bother looking at that kind of code? The thing is, where there is C++, there is C++ standard library, like mostly. And C++ is used everywhere. So even if you manage to do like a very small, like micro optimization there, the overall impact on the like software industry as a whole is huge. You can see all the big companies are here, all the smartphones, airplanes, web browsers, everywhere. C++ runtime is basically everywhere. In this presentation, I'll be talking about like 4 different like axes, like dimensions of where we have opportunities to do some optimizations. These are all the optimizations that I'll discuss here are not there in the library as well already. So these are like open opportunities. If you would like to do some optimization based on the things I shared, please feel for free and go ahead and do them, because it will help so many people, literally billions of people. I'll talk about, I'm basically showing problems here. I will just give guidelines on solutions, but I'm not showing the exact code which will solve this problem. Otherwise, I would just have committed the code already, right? So the first thing I'll talk about is a couple of issues in the standard library containers, then algorithms, and then source code annotations, and then some specific compiler optimizations. So yeah, here's the first taste of how C++ looks like when it is in C++ standard library. You can see all these underscores and weird names. This is a string find algorithm, but this is the R find, where you're searching from the end of the string and you want to find a substring from the last position. And this algorithm is super slow, as if you have looked into the C++, one second, yeah. If you have looked into the string search algorithms before, we have quite efficient implementations, but this implementation here is possibly the slowest you can even imagine. So like, I think anything you write will be better than this one. And why I can say this, because I almost like 4 years ago, I optimized the string find routine where we search the substring from the beginning. And I was lazy and I didn't do for the other ones. So basically you can just look at the find and incorporate into the string R find. And the performance improvement is not in percentages, it is in orders of magnitude. You can get like 10x, 20x performance improvement. So, and if you do say like some paper napkin calculation, it'll and on of the energy cost, it'll be like, it could be like millions of dollars per year if you just optimize this 10 lines of code. Similarly, the string find has other variants like find first off, find first not off, those things. All of them are not optimized. Only the string find is optimized because I basically had enough time and patience to do that one. Do we have messages in the chat thread? Oh. Oops.
That was me.
Okay.
Sorry.
All right, moving on to the next slide. The next one is IO stream and locale. I have bundled them together because they most of the time, if you start following the call graph, many of the calls from IO stream will go to the locale, because when we are parsing a stream of characters, there is like locales are involved. And the thing is, most of the time we are parsing like the ASCII letters, right? And but this locale is written to incorporate all kinds of various things, and which nobody even uses. And you have all kinds of virtual functions and interactions. They just slow down the performance. I'm sharing a couple of examples here, which are quite interesting. So when we are parsing a string, we are looking for, like, let's say we are parsing a number. So we basically, what we do is we take one character from this buffer and we compare with a predefined set of valid characters. And those are called atoms in the language of standard library. So here you have, like, you can see the array like hex digits. You have ABCD and capital ABCD and 0 to 9. These are the valid characters, right? So when you take a character from the buffer and you compare this with one of these, right? In libc++, we do as like a linear search algorithm. We start finding from beginning and go to the end to find if there is a valid character or not. Like there is, I don't think there is a reason to do a linear search here. Like there are like quite efficient ways to search, but libc++ does that. So it is an ON algorithm, super slow. So anytime you are like feeding a file or feeding a buffer, reading from the command line or something, or reading from a file, you're basically, this algorithm will kick in, and it is a slow algorithm. libc++ and libstandard C++ have different ways of representation. Like this atom string, you see the plus sign in libc++ is in the middle, the last line. And in libstandard C++, the plus and minus sign are in the beginning. And it may look like benign or many of these things, but just if you think about it for a minute, right? Let's say, take the example of libstandard C++. You have minus, plus, then small x, then capital X, then 0. Now, if we are doing a linear search, like you have to go to 5 steps to go to 0, right? It may look very cheap, right? But the thing is, 0 is the most common digit. It is undisputable. So for finding 0, you're just always searching for useless characters. So maybe we should rearrange this string to a better, like a slightly better way. So this is the problem. Another problem in libstandard C++ is in this array hex digits, right? So you have A, B, C, D, E, F, A, B, C, D, E, F, then 0. And the next line you have decimal digits, which is a pointer with an offset of 12. Basically, it'll point to 0 here. Now, the pointer decimal digits may not be perfectly aligned because you're skipping 12 characters. So is it in the beginning of the cast line? I don't know. On different machines, it will be different. And we really want to, like, 0 should be the first character, right? And it should be very perfectly aligned because we will be looking for 0 like a lot. So there can be performance issues here. These are like extremely micro optimizations, but as I mentioned, when you're talking about standard library, it is used so many times that it has a very useful impact. Okay, moving on to the standard library algorithm. I have very little to say here. the most common algorithm, right? It's the sorting algorithm. And libc++ is not does not guarantee n log n time complexity. The C++ standard itself requires n log n, but libc++ quicksort does not give you that one. So this is another opportunity to do some optimization here. The next one in the standard library is the standard find. Find is a linear search algorithm. What I wanted to share here is if you're using Clang, Clang has a, like by default, it will unroll with like factor 5. I don't know why 5 is there. 5 looks like an odd number. And then in lib standard C++, it'll unroll by 8. And when you use GCC, GCC will unroll by 4. So you see like there are 3 different variations here. When you have a same C++ program, if you use Clang with lib standard C++, if you use Clang with lib C++, or if you use GCC with lib standard C++, you might get totally different performance just because the unroll factors of those compilers are different. And here's the Godbolt link if you want to try. You can see all this, what I have shared. All right, so moving to the third category of source code annotations. What do we mean by annotations? Basically, the compiler provides a way to annotate functions or lines of code where you can give a hint to the compiler that what is a desired behavior from a user's point of view. And that can be used to help compiler generate more efficient code. The most common one is annotating the non-returning functions. So let's say there is a function which aborts the program. So obviously that function, when you call that function, the program is going to terminate. It is not going to return. That function does not return. If the compiler knows about it, it can basically assume that that piece of code is cold and it can generate a better code. One example in the C++ standard library is there are 2 functions, throw length error and throw out of range. These are the functions that are called when we, let's say, if we do a pushback on vector and like there is not enough memory. So we can get one of these errors. I forgot which one is which. So these 2 functions are not annotated with no except like non-returning functions. There are many functions like this and all of them are annotated, but only these 2 were not there. And so I like a few years back, I analyzed the standard library and put those annotations everywhere, but probably I missed these 2. So if you want to have a short diff, this was one good one. Another one is annotating the conditionals with built-in expect. Or in C++20, we have this like annotations with like likely. If you put likely, then the compiler will assume that this branch is more likely. There is good. All right. So this is the function called xsgetN. This is again from the IOStream library, the stream buffer basically. And this is the while loop where the first part is called more often, because this is the part where we keep copying, and the next else if and else part is called very rarely. So if you provide a hint to the compiler would basically generate better code here. The next one is annotating the pointers with restrict. Let's say we take an example of string copy. In string copy, you have a destination and source, right? And then we make a copy from one buffer to another. Now this string copy calls char traits copy. And if you see, the signature of char traits is the char type S1 and S2. You have destination and source and the number of characters you want to copy. We know that the string copy when we, the C++ standard library specifies that string copy cannot be called on the same string. So the range will not be overlapping. But the char traits copy does not know about this information. So char traits copy basically calls, I think it calls mem copy or mem move. So it does not know about the that these two pointers may never alias. So that information is lost. We need to put like restrict keyword to let the compiler know about that part. The third popular annotation is no except. Basically, when we put no except in a function signature, it tells the compiler to not generate exception handling code for that function body. What that means is if there is an exception, that if there is an exception thrown from the function body, there will not be a code for stack unwinding. So that helps with code size. And in many applications, we do not use exceptions at all. So in those cases, we are better off just adding no except. In C++ standard library, we are fairly consistent with no except functions, functions which actually does not throw. But what about the functions which may throw, right? Now, for them, the compiler will generate exception handling code. But if my application, I'm not interested in exception handling code. I just want the program to abort anyways. So what should we do? So I'm basically suggesting an approach here where you have like some macro where an application writer can define this macro and the compiler will do the right thing based on that macro. People who want exceptions, they are happy, as well as people who do not want exceptions, they are good as well. The last attribute is the visibility attribute. This is a tricky one. What happens is, by default, any function is externally visible, right? Any function can be called from like basically anywhere in the program. But what if a function is only like you really don't want that function body to be visible like from other places? That to achieve that, we basically in C++ we write static keyword, right? And in terms of compiler attributes, that is called attribute internal. What happens is when we put attribute internal, the compiler does not generate the indirection pointer. Basically, there is an entry in the global the PLT, and the PLT entry is not there. So that saves code size and one indirection as well. So in that case, we can totally put attribute internal in many of the C++ standard library functions and basically save improve performance by reducing one indirection. These are a couple of interesting questions, like what is the default visibility of the C++ programs? The answer is default visibility. Like there is attribute default, which is the default behavior. And the second question is, what does F visibility hidden do? So F visibility hidden will basically mark, will make the function as hidden for a specific shared library, not for the translation unit. So it is DSO visible. And to learn more about this, you want to check out this documentation. They have a lot of good details there. All right, moving on to the compiler optimizations. When we use the C++ standard library, many of the functions and like data structures and algorithm are header only. But there are many functions which are in the lib standard C++, that libstdc++ or libc++, which is called as a runtime, right? And those libraries were compiled with some optimization flag, and they may be different across different operating system versions. But when we compile our application, we compile with a different optimization. We have different requirements in mind, like we care about performance, or we care about code size, or we want like the most aggressive performance, like O3, O fast, right? But we do not get those advantage of the same optimization flag in the runtime, right? So we are losing performance like for free. This is an open problem. I don't know what is the solution here. Like one solution is, if you really care about performance, you want to ship the standard library with your binary. So statically compile that binary into your program. And then you can choose whatever flag you want. And the entire library as well as your application are compiled with your choice of optimization flags. That may give you like extra performance. Of course, that is extra maintenance, but if you're interested. Another issue is inconsistent exception handling flags. Let's say I do not care about exceptions, so I may compile my program with F no exceptions. But the C++ standard library itself was compiled with F exceptions, like the default ones, which comes with any operating system. So you're not there is a discrepancy here, and there are correctness issues associated with this. So we need to have like I'm not 100% sure here that if there is a correctness issue with the C++ standard library, because I do not like look at every line of code which are in the CPP files. But in general, if you have two translation unit where one is compiled with exception and other is not, you may end up with correctness issues. So we need to like some careful investigation is required here. And a whole lot of other compiler optimizations. I would touch like very briefly on each of these. The first one is whole program devirtualization, or like these days when we are this link time optimization is getting more and more popular, like the thin LTO, those things. Now, if we choose to build the library, the C++ standard library with the application, we can get a lot of advantage there. Like we can basically inline many cross translation unit functions. We can do like devirtualization, basically resolving the indirect function calls. That is called devirtualization. Then now we may will be able to inline like more important functions. The third one is auto vectorization. I guess Stefan has touched like in great detail how vectorization is important. We can achieve that one also. The fourth one is pretty interesting: loop idiom recognition. In libc in the standard libraries, there are many like functions which can be lowered into like C library calls, but they are not. Compiler may do some optimization, like compiler may do some vectorization there or unrolling. But if we could lower them to these like memset or memcopy style functions, we will get huge performance improvements. But the loop idiom recognition of like LLVM misses many of these opportunities. If you want to know more about it, like I presented some of the examples in the LLVM developer conference, the previous one. The fifth one is loop unrolling. As I shared, different compilers have different unroll factors, the default ones. So just by changing the compiler, you might be getting different performance for the same code. And the last one is jump threading. And this one is tricky to get, but there are opportunities of having jump threading. And how I can say that by just using a simple grep command. Jump threading, so what is jump threading? First, let me give an example. Let's say you have a chain of branches, like you have if else and nested if else, right? It is possible that the same condition can like a condition, a decision in the previous case can be used to do some optimization in the nested case. Right? It can happen because of the value range propagation, or it can happen because of just constant propagation itself. Now, the optimization that helps do this is called jump threading. And the classical example is like applications with a lot of branchy code. And when we have a lot of inlining going on, you find like very interesting opportunities. LLVM has jump threading. It is very primitive, but it does some things. GCC also has jump threading, but it is like quite mature. There is a way to do jump threading in the back edge of the loop. Like let's say you have a code which parses a piece of code, the parsers, right? The classical approach of a parser would be you have a for loop and inside you have a switch statement. So this back edge is very hot because every time you must take a back edge and you do a lot of branches again. So if you do jump threading across the back edge, you get like very nice performance improvements. And if you use profile guided optimization, you can get like even more improvements. Like you can get like 30% kind of improvement here. I think there's an opportunity here because I see a lot of switch statements. Switch statement means there is an opportunity for jump threading. It is like as obvious as this one. So that's about it. I have like shared some additional reading. This is from like 4 years ago. I presented it at CPP now. It shows more systematic analysis of C++ standard libraries. So you might find a lot of interesting experiment results. Today's presentation was a lot of hand waving, but this has like concrete data and like more analysis there and some references. Thank you.
Perfect. Thank you very much. I don't see any questions right now in our chat. So one thing I would ask is how should people kind of approach this? Like, what would you suggest, given that you did it yourself a couple of times? Yeah. How you find those? Like you showed these after the fact, right? And then it's kind of obvious. Oh, here you need a no return attribute, or here you need this. But how do you come up with that?
The most obvious approach is to read the code and have some patience. That is what I did mostly. And of course, like the things I have shared, like many of these are available online, like in LLVM mailing list. People have complained, and you go to LLVM Bugzilla or GCC Bugzilla, you might see some of the instances of these there. But like I've been like basically I'm kind of mentally collecting all these for like some period of time. So that's why you have a comprehensive list here. If someone wants to just get started, just take this slide and start putting patches, basically.
Okay, that sounds good. And maybe one other question in that kind of ties in with what we've seen in the talk before. Do you think we should make the compiler standard library aware, or do you think we should approach it with more kind of like the attribute angle and try to compose attributes to get the right behavior?
I think the using attributes is more scalable, because if you just make a compiler like library aware, then how much intelligence are we going to put in the compiler? That is a lot of work. But putting attribute is like very generic, and users can also use them, those attributes, right? Like your work on the attributor framework, right? When we do fixed point analysis, that applies to like basically every code, and that is pretty amazing.
I mean, the argument that if you have source attributes, then people can use them for their version of the standard library or algorithms is probably a very strong one. So, yeah. So if you implement your own find or your own vector for whatever reason, you can kind of do the same trick, and which seems reasonable.
Yeah.
Okay, great. I think we reached the end of our one-day workshop, just in time. Thanks again for your talk, and also I would like to thank you for doing most of the organization work for the workshop. That should be said.
Yeah, like we could get like open the floor for like a couple of minutes for everyone if they have like suggestions, or they want to talk about something, what they liked or they wanted us to improve. Please share. Like you can raise your hand and I'll let you speak.
Right. While we're waiting for people to gather their thoughts, you mentioned earlier we will have the recordings on YouTube, right?
Yes, yes. So like once, I guess we'll get the link, like the video link from the CGO, and I'll have to download the video from somewhere, and then we'll put them on YouTube.
Okay, perfect. We could try to put them in the LLVM channel. That would probably give them nice visibility.
Yep.
People can also kind of reach out to the speakers through the VOVA app. We have an LLVM channel there. There's also a couple of new, like the upcoming LLVM conferences are also listed in the VOVA app. So take a look at that.
Yeah.
I guess we should thank everyone that stayed, and we're aware that the time zone difference made that pretty hard for quite a few people. It's good that we have recordings. Aditya, you want to say a few words and then we end this?
I just want to thank everyone to like sparing their time for to listen to this exciting talks, and the speakers, they put in a lot of effort here to basically share their work. We like this conference to be like as easy for developers to present, so we do not require like a proceeding. They don't have to do a lot of write-up, because as an engineer we are already busy with so many things, and putting up presentation is already a good amount of work. So yeah, thank you for presenting all the we had college students, we have university folks, and we have industry folks. So thanks everyone to put their thought together and in a very useful content. We really appreciate your work.
Exactly. Right. Okay. Then I hope everyone has a great rest of their day, however long that is, and enjoys the rest of the conference, CGO, CC, and what else they will visit. Thanks again, Aditya. And
awesome. Thanks. We'll end that meeting then.
yes.